Welcome, curious minds and sleepy thinkers. You've found a soft place to land where the questions are big and the pace is slow enough not to jolt you out of your pillow cocoon. Tonight, we're going to tiptoe into one of the most mysterious questions ever asked. What is the universe? We won't be rushing through equations or facts. Instead, we'll gently explore its nature, drifting through grand ideas and the unsolved mysteries that whisper at its edges. This isn't a race through complex theories, but more like floating through a galaxy of thoughts with a warm, comforting cup of chamomile tea by your side. The universe. Just the sound of the word can evoke a vastness that humbles us, a mystery so profound it almost feels like a dream. It stretches beyond our grasp, beyond the most powerful telescopes, beyond the furthest reaches of our imagination. It is, in its essence, the ultimate frontier, not merely for our grand scientific instruments or our daring rockets, but for our very human quest for understanding. Since we first looked up at the night sky, perhaps huddled around a fire long ago, we've been captivated by its silent, shimmering beauty. This ancient wonder has sparked in us a deep desire to comprehend our place within the grand cosmic ballet, to find meaning in the vast, swirling expanse. And as we continue this journey of looking up and wondering, we find that it is as much a discovery of ourselves as it is a revelation of the cosmos. Imagine for a moment the universe as an immense, intricate tapestry. Each thread, each color, each shimmering detail contributes to a whole that is far grander than any single part. At its heart, this cosmic tapestry is woven from the very fabric of space and time, intertwined with countless galaxies, each one a luminous island containing billions upon billions of stars, and around those stars, a silent, swirling dance of planets and moons. The sheer number is almost impossible to hold in our minds. If you were to count every grain of sand on every beach on our little blue planet, you still wouldn't come close to the number of stars estimated to exist in the observable universe, and each star a potential sun to its own collection of worlds. This is the observable universe, the part of this grand tapestry from which light has had enough time to reach us. It is a testament to the staggering complexity and profound majesty of nature, a masterpiece unfolding slowly over billions of years. But what whispered into existence this magnificent creation? Scientists, in their quiet, methodical way, have pieced together a story, a leading explanation for the universe's beginning. They call it the Big Bang. But let's gently set aside any thoughts of a loud, destructive explosion in a void. Instead, imagine it as an extraordinary rapid unfolding, a monumental expansion of space itself. Think of it like this. Take a deflated balloon and draw tiny dots on its surface with a soft pencil. Now slowly and steadily, begin to inflate the balloon. What happens to the dots? They move away from each other, not because they are crawling across the rubber, but because the very surface they rest upon is stretching, expanding, carrying them further apart. This is a gentle metaphor for our universe's inception. From an infinitely dense, unimaginably hot point, a single singularity, space itself began to stretch and unfurl like a cosmic flower blooming at an accelerating pace. And in this unfurling, the universe evolved into the cooler, vast cosmos we observe with our telescopes today. This singular event marks the very beginning of everything we know, all space, all time, all matter, and all energy. How do we know this story, this grand narrative of the universe's birth? It's not from a dusty old book, but from the echoes, the whispers that still travel across the cosmos from that primal moment. Scientists, with their patient observations, estimate the age of this magnificent unfolding at approximately 13.8 billion years. This number isn't plucked from thin air. It's a careful calculation derived from measuring the motion of galaxies, much like observing how quickly those dots on our cosmic balloon are moving apart. And perhaps even more profoundly, it comes from studying the cosmic microwave background radiation, a faint ancient glow that permeates the entire universe, This radiation is the very afterglow of the Big Bang, the primordial light that was released when the universe finally cooled enough to become transparent, like a thick fog suddenly clearing. It's like finding an ancient photograph of the universe as an infant, allowing us to peek into its earliest moments and understand its origins. But as we gaze upon this cosmic tapestry, a profound mystery emerges, one that whispers of unseen forces and hidden influences. When scientists meticulously add up all the stars, all the galaxies, all the nebulae, all the ordinary matter that we can see, touch, and measure, they find something astonishing. This visible, familiar stuff, the very building blocks of ourselves and everything around us, accounts for only about 5% of the universe's composition. Just a tiny fraction. Imagine trying to understand a magnificent sculpture by only seeing a whisper of its surface, or listening to a symphony and only hearing a few scattered notes. The vast majority of the universe, the grand bulk of it, remains shrouded in mystery, hidden from our direct view. This hidden majority is comprised of two enigmatic entities, dark matter and dark energy. Their names alone hint at their elusive nature, like shadows dancing at the very edge of our perception. Dark matter, making up about 27% of the universe, does not emit, absorb, or reflect light. It is utterly invisible to our telescopes, a ghost in the cosmic machine. Yet its presence is profoundly felt through its gravitational influence. Think of it as the unseen cosmic glue holding galaxies together, shaping their magnificent spiral arms, and orchestrating the dance of galactic clusters. Without this unseen gravitational scaffolding, galaxies would simply fly apart, unable to maintain their delicate structures in the face of their own rapid rotation. It's like trying to build an invisible house where you can't see the walls or the beams, but you know they must be there because the roof isn't falling down. Dark matter is the invisible architecture of the cosmos, providing the necessary gravitational pull to sculpt the universe's grand structures. And then there is dark energy, an even more mysterious force, accounting for roughly 68% of the universe's total energy content. If dark matter is the cosmic glue, then dark energy is the cosmic push. It is the enigmatic force driving the universe's accelerated expansion, a discovery that in 2011 rightfully earned a Nobel Prize in Physics. Imagine you're inflating that balloon again, but this time you feel an unseen hand gently yet powerfully pushing the surface outwards from every point, making it expand faster and faster rather than slowing down. That's dark energy at work. It doesn't seem to clump or cluster like matter. Instead, it appears to be uniformly distributed throughout space, a subtle, persistent pressure that is slowly, inexorably driving the galaxies further and further apart. The nature of dark energy remains one of the most profound puzzles in all of science, challenging our deepest understanding of fundamental physics. It's like finding a mysterious, quiet current in the middle of a vast ocean, a current that seems to be speeding everything up, and we don't quite know why. Understanding these hidden components, this vast unseen majority invites us to ponder the fundamental nature of reality itself. It gently nudges us to consider our own place within this grand cosmic design. Weaving together the threads of cosmology, the study of the universe as a whole, with the timeless questions of philosophy. Philosophers and scientists, hand in hand, delve into the profound inquiries about the universe's ultimate origin. Where did it all truly begin beyond the Big Bang? What is its ultimate fate? Will it expand forever? Or will it eventually draw back into itself? And what are the hidden laws that govern its behavior? These elegant mathematical whispers that dictate the dance of galaxies and the flicker of distant stars. This quiet quest for knowledge constantly challenges our perceptions, pushing the boundaries of what we believe to be true. It compels us to consider not just the elegant mechanics of celestial bodies, the graceful orbits of planets, the fiery lives of stars, but also the very essence of existence itself. It's a gentle invitation to explore concepts that stretch our minds, such as the multiverse theory. This captivating idea suggests that our universe, with its billions of galaxies and its unique set of physical laws, might simply be one bubble among countless others, each possibly operating under its own distinct set of cosmic rules and constants. Can we even imagine such a grand tapestry, where our universe is just a single precious thread in an infinite loom? These are the questions that keep us awake, not with worry, but with a quiet sense of wonder, as we stand at the precipice of the known, gazing into the vast unexplored mystery that is the universe. The journey to determine the age of the universe is a story woven through centuries of patient observation and brilliant flashes of theoretical insight. It's a narrative that traces back to the earliest civilizations, to those first quiet moments when humans looked up at the stars and dared to ponder their origins. What were those sparkling points of light? Were they gods? Were they holes in a cosmic curtain? These ancient inquiries, born of simple wonder, were the first tender shoots of what would become a deep scientific pursuit. However, the scientific endeavor to pinpoint the universe's age truly began to take shape in the 20th century, a period marked by astounding breakthroughs in physics and astronomy. It was as if humanity, after centuries of merely gazing, had finally found its proper tools and its true language for deciphering the cosmos. The pivotal moment, a genuine turning point, arrived with Edwin Hubble's observations in 1929. Imagine, if you will, the quiet dedication of a lone astronomer peering through the lens of a telescope, meticulously recording the light from distant galaxies. And what he saw, what he measured, was a profound revelation. Galaxies were not static islands in a fixed universe. Instead, they were moving away from us, almost as if the very fabric of space between them was stretching. This profound discovery, like the gentle unwinding of a cosmic clock, laid the essential groundwork for the Big Bang theory, which swiftly became the leading explanation for the universe's origin. It painted a picture of a cosmos that was not eternal and unchanging, but one that had a definitive beginning, a moment when everything we know sprang into being. By carefully measuring the speed at which these galaxies recede from us, a phenomenon we often refer to as redshift, where light from distant objects appears stretched to longer, redder wavelengths, much like the pitch of a siren dropping as it moves away, astronomers could infer the rate at which the entire universe was expanding. This rate, a fundamental cosmic constant, became known as the Hubble constant. Early estimates of this constant, though groundbreaking, hinted at a somewhat younger universe. But as our ability to measure the universe's expansion grew more precise, as our instruments became sharper and our understanding deeper, the estimated age was slowly, patiently revised upwards. It's like trying to guess the age of a very old tree by looking at its rings. The more clearly you can see the rings, the more accurate your guess becomes. The late 20th and early 21st centuries ushered in a new era of cosmic precision. The advent of more sophisticated technology like the Hubble Space Telescope, our eye above the atmospheric blurring, and later the Planck satellite, our ultra-sensitive ear listening to the universe's ancient whispers, refined our understanding of the cosmic microwave background radiation to an unprecedented degree. These sensitive instruments provided an incredibly clear picture of the universe's early moments, moments of almost perfect uniformity, dotted with tiny, delicate ripples. These ripples, like the first disturbances in a calm pond, were the seeds from which all future structure would grow. By analyzing these ancient patterns, we were able to narrow down the Hubble constant to a far more accurate value. The data from the Planck satellite, released in the 2010s, was particularly pivotal. Its measurements of the cosmic microwave background, taken with breathtaking precision, provided the final crucial pieces of this cosmic puzzle. Leading us to our current best estimate, the universe is approximately 13.8 billion years old. It's a number that feels both incredibly specific and impossibly vast, a quiet testament to billions of years of cosmic unfolding. But the determination of the universe's age doesn't just rely on peering into the echoes of the Big Bang. It also draws upon our understanding of the life cycles of stars. Imagine each star as a tiny flickering clock, burning its nuclear fuel in a predictable way. By observing the oldest stars within globular clusters, which are dense ancient groups of stars like cosmic beehives held tightly together by gravity, astronomers can infer a minimum age for the universe. These stars, some of the very first to form after the Big Bang, offer us a kind of stellar clock to gauge cosmic history. They are the venerable elders of the universe, their long, slow lives providing a lower limit to the age of the cosmos. The oldest among these stars are found to be nearly as old as the universe itself, perhaps around 13 billion years. They whisper to us tales of the earliest moments, confirming the timeline pieced together by other cosmic clues. It's like finding a very old, beautifully crafted timepiece, still quietly ticking, reminding us of the immense stretches of time that have passed since the universe began its grand journey. As we gently delve further into the mysteries of the cosmos, a fascinating concept emerges that builds upon our understanding of the universe's immense vastness and its ancient age, the observable universe. This term refers to the portion of the entire universe that we, from our tiny vantage point here on Earth, can actually see or detect. It's like standing in a vast, dark forest at night with a single flashlight. You can only see as far as the beam of your light can reach. Our cosmic flashlight in this analogy is the very light that travels across the universe, and its reach is limited by two fundamental cosmic speed limits: the speed of light itself and the age of the universe. Light, you see, travels at a finite speed, a breathtakingly fast, but still measurable pace of approximately 299,792 kilometers per second in the vacuum of space. This means that when we look out at a distant star or galaxy, we are not seeing it as it is right now at this very moment. Instead, we are seeing it as it was when the light left it. It's like looking at an old photograph. The light from distant objects takes time, often billions of years, to reach our eyes. So the farther away an object is, the further back in time we are looking. The observable universe, then, is essentially a cosmic sphere, with our Earth nestled precisely at its center. Its radius, the furthest distance from which light has had enough time to reach us, extends outwards to about 46.5 billion light-years. This number might seem a little puzzling at first glance, especially when we remember that the universe itself is only about 13.8 billion years old. How can we see light from 46.5 billion light-years away if the universe is younger? The answer to this gentle paradox lies in the ongoing expansion of the universe. Imagine once more our cosmic balloon stretching continuously. As light travels from a distant galaxy towards us, the space it is traveling through is also expanding. So by the time the light finally arrives, the galaxy it originated from is now much, much farther away than it was when the light first set out. It's as if a message started its journey from a point 13.8 billion light-years away. But during its long voyage, the distance itself expanded, so the current distance to that starting point is now much greater. Thus, this 46.5 billion light-year radius marks the furthest cosmic shoreline from which light has had enough time to travel to us since the universe began its expansion approximately 13.8 billion years ago. It's our ultimate cosmic horizon, beyond which the light simply hasn't had enough time to arrive. This distinction between the observable universe and the entire universe is absolutely crucial. Like the difference between seeing a small part of a vast ocean and knowing the ocean continues far beyond your sight, while the observable universe is the part we can see the latter. The entire universe encompasses all of space, all of existence, and much, perhaps even most of this entire universe remains beyond our current observational capabilities. Its true size remains unknown. It could be infinitely large, stretching on forever in every direction, or it could be wrapped back onto itself in a way that defies our standard notions of flat linear geometry, much like the surface of our Earth, which appears flat to us, but is actually curved. The mystery of the entire universe's true extent is a question that gently beckons us into the realm of profound, unanswered questions. Within this vast observable sphere, this cosmic vista that we can glimpse, there are an estimated 2 trillion galaxies. Think of that number for a moment. 2,000 billion galaxies, each one a magnificent island of stars, harboring millions to trillions of stars, along with an even greater number of planets, asteroids, and comets. This staggering count comes from deep sky surveys and patient observations made by telescopes like the Hubble Space Telescope. Hubble, perched high above our atmosphere, has peered back in time like a gentle time traveler to glimpse the universe as it was shortly after its birth, revealing faint, distant galaxies that are barely more than whispers of light. These observations have not only expanded our sense of the cosmos's immense scale, but have also provided invaluable insights into the very processes of formation and evolution of these grand cosmic structures, telling us how these magnificent star cities came into being and how they have changed over billions of years. Understanding the observable universe also involves grappling with concepts that stretch our minds, such as cosmic inflation. This is a theory, a powerful and elegant idea, suggesting that the universe underwent an almost unimaginable exponential expansion in its first tiny fractions of a second after the Big Bang. Imagine a microscopic speck of dust suddenly inflating to the size of a mountain range in less than the blink of an eye. This incredibly rapid stretching of the fabric of space itself led to the vast distances between galaxies we observe today. It's a concept that bridges the seemingly disparate fields of cosmology, the study of the universe at its largest scales and theoretical physics, the quest for the fundamental laws that govern reality. Inflation offers beautiful explanations for the remarkable uniformity of the cosmic microwave background radiation, explaining why the universe looks largely the same in every direction, and also helps account for the large-scale distribution of galaxies across the sky, explaining why they cluster together in intricate patterns, rather than being spread out randomly. It's a quiet whisper of a theory that explains some of the grandest features of our cosmic home. In exploring the observable universe, we are gently confronted with the limitations of our current technology and the unwavering laws of physics. The light from objects beyond the observable universe, from galaxies and stars that exist outside our cosmic flashlight's beam, has simply not yet had enough time to reach us. These regions remain beyond our current sight, silent and unrevealed. Yet this is not a cause for despair, but for quiet anticipation. Advancements in telescope technology and innovative observational techniques continue to gently push the boundaries of what we can see, little by little, unveiling more and more about the universe's structure, its rich history, and the fundamental elegant laws that govern its every motion. Each new instrument is like a brighter, more focused beam on our cosmic flashlight, revealing new wonders in the vast, dark forest. It is a slow patient, unveiling a never-ending journey of discovery that promises to keep our sense of wonder alive for generations to come. So how do we observe this vast cosmos stretching billions of light years across? How do we listen to the ancient whispers of light that began their journey before our world even formed? Observing the universe is a multifaceted endeavor, a grand symphony of technology and methodology, each instrument and technique designed to capture a different aspect of the cosmic dance. At the very heart of this exploration lie telescopes, instruments that have been refined and transformed over centuries. From the simple, wondrous optical tubes used by Galileo Galilei, which first showed humanity, Jupiter's moons dancing around it, to today's incredibly sophisticated observatories. These tools are our eyes into the infinite. They allow us to detect not just the visible light our eyes can perceive, but a vast spectrum of electromagnetic radiation, from the long lazy waves of radio through the warmth of infrared, the subtle glow of ultraviolet, and finally, to the energetic flickers of X-rays and gamma rays. Each of these different kinds of light tells us a unique story about the universe, much like different instruments in an orchestra contribute to the full richness of a melody. Optical telescopes. The most familiar kind are designed to collect visible light. They are the instruments that paint for us the familiar images of sparkling stars, swirling galaxies, and ethereal nebulae within the observable universe. They are our primary window into the part of the cosmos that our eyes, if only they were powerful enough, could see. These telescopes have been instrumental in our initial forays into space observation, allowing us to map the heavens and begin to understand the positions and movements of celestial bodies. Think of them as giant, refined eyes, gathering every precious photon of light to reveal the hidden beauty of the night sky. However, to truly understand the universe's full complexity, we've had to venture far beyond the visible spectrum. The cosmos is not just a painting of visible light. It's a symphony played on many different wavelengths. For instance, radio telescopes, with their immense dish-shaped antennas, are designed to detect radio waves emitted by distant cosmic objects. These waves are much longer than visible light waves, and they can travel through vast clouds of dust and gas that would block our optical view, like a voice carrying through a thick fog. These remarkable instruments have unveiled phenomena utterly invisible to optical telescopes. They were crucial in discovering the cosmic microwave background radiation, that ancient whisper we spoke of earlier, a relic from the universe's infancy that provides crucial, undeniable evidence for the Big Bang Theory. It's like listening to the echoes of the universe's very first breath. Radio astronomy allows us to peer into the dark corners of the universe, revealing secrets hidden in the invisible realm. Then there is infrared astronomy, which opens another unique window, allowing us to observe celestial objects that are often hidden by dense clouds of dust that visible light simply cannot penetrate. Imagine trying to see through a thick, dusty curtain. Visible light would simply bounce off, but infrared light, with its longer wavelengths, can often pass right through. This has revealed new stars in the very process of formation, nestled deep within their dusty nurseries, and has allowed us to glimpse distant galaxies that are obscured from view in the visible spectrum. Infrared light often tells us about cooler objects or regions where light is absorbed and re-emitted as heat. Similarly, X-ray and gamma-ray astronomy allow us to study the most high-energy processes in the universe, events of incredible violence and power, such as the swirling matter around black holes, the explosive deaths of massive stars, and the superdense remnants of neutron stars. These energetic forms of light offer us insights into the most extreme and energetic events in the cosmos, like catching glimpses of a cosmic fireworks display that is otherwise invisible. The greatest leap in our observational capabilities, however, has been the advancement of space-based telescopes. Our Earth's atmosphere, while vital for life, acts as a shimmering, distorting veil, absorbing much of the electromagnetic spectrum and blurring the light that reaches us. Instruments like the Hubble Space Telescope, majestically orbiting outside Earth's atmosphere, have provided us with images of unparalleled clarity and detail, free from any atmospheric distortion. It's like taking off blurry glasses and suddenly seeing the world in sharp focus. The James Webb Space Telescope, JWST, launched to succeed, Hubble represents the next generation of this incredible technology. It focuses primarily on infrared astronomy, aiming to observe the universe's very first galaxies, those whispers of light from the cosmic dawn, and to delve even deeper into the mysteries of how stars and planets form, seeing through the cosmic dust like never before. But observing the universe extends beyond merely collecting electromagnetic radiation. The cosmos communicates with us in other ways too. Neutrino observatories, often buried deep underground or submerged in ice, detect nearly massless particles called neutrinos. These ghost particles interact so rarely with ordinary matter that they can stream right through entire planets, carrying clues directly from the hearts of stars and the violent aftermath of supernovae. They offer a unique unhindered glimpse into processes that are otherwise obscured, like listening to a secret conversation no one else can hear. And then there are gravitational wave observatories, such as LIGO Laser Interferometer, Gravitational Wave Observatory. These revolutionary instruments have opened an entirely new avenue of exploration by detecting ripples in the very fabric of space-time itself. These ripples, generated by unimaginably cataclysmic events, like the collision of black holes or neutron stars, are like faint echoes of cosmic earthquakes. This method provides a truly unique perspective on the universe, enabling us to study phenomena that emit little to no light, giving us a completely different kind of sense for the cosmos. The process of observing the universe is an ever-evolving field, driven by human ingenuity, relentless technological innovation, and profound theoretical advancements. As we delve deeper into our cosmic journey, our natural curiosity leads us to ponder the very limits of our observation. We've discussed what we can see, but what about what we cannot see? Why can't we see beyond the observable universe? This isn't a simple question of building a bigger, more powerful telescope. It touches upon fundamental aspects of physics and the very nature of the universe itself, reminding us that there are inherent boundaries to our perception. The observable universe, as we gently established, is defined by the farthest reaches from which light has had enough time to travel to us since the universe's inception, approximately 13.8 billion years ago. This boundary is not a physical wall, not a shimmering glass dome at the edge of space, but rather a limitation imposed by the finite speed of light and the age of the universe. Imagine you are trying to see a light from a ship that sets sail across an ocean. If the ship has only been sailing for an hour, you can only see the light from as far as it could travel in that hour. In the cosmos, our ship is the light itself, and the sailing time is the age of the universe. Light travels at a constant, unwavering speed of about 299,792 kilometers per second in a vacuum. This speed sets a cosmic speed limit, a fundamental boundary dictating how far we can possibly see into the universe. Since the universe is about 13.8 billion years old, the farthest light we can observe has traveled from a distance corresponding to this age. This allows us to see as far back as the cosmic light horizon, a concept much like the horizon you see at sea, but in 4 dimensions. This horizon marks the edge of our observable universe, approximately 46.5 billion light-years away from us today. The discrepancy, as we gently noted, between the universe's age, 13.8 billion years, and the radius of the observable universe, 46.5 billion light-years, arises directly from the expansion of the universe. It's as if the road the light travels on is continuously stretching beneath its cosmic feet. So by the time the light from a very distant galaxy finally reaches us, the actual distance to that galaxy due to the continuous expansion of space, since the Big Bang is far greater than the simple product of its travel time and the speed of light. Beyond this horizon, beyond this cosmic shoreline, lies the unobservable universe. This vast realm remains hidden from our view, simply because the light from these regions has not yet had enough time to reach us. It's like waiting for a very slow, very distant message that hasn't arrived yet. Furthermore, the relentless expansion of the universe, driven by that mysterious force we call dark energy, causes distant galaxies to recede from us at speeds that actually increase with distance. At a certain point, a cosmic boundary known as the Hubble length. This recession speed exceeds the speed of light. Now, this doesn't violate Albert Einstein's profound theory of relativity, which wisely prohibits objects within space from moving faster than light. Here's the subtle but important distinction. It's not the galaxies themselves that are racing through space faster than light. Instead, it's the fabric of space itself that is expanding, carrying the galaxies along with it. Imagine again our expanding balloon. The dots aren't moving on the surface faster than light, but the surface itself is stretching so quickly that two very distant dots can appear to recede from each other at speeds greater than light. It's a concept that stretches our everyday intuition, gently reminding us of the universe's extraordinary nature. The concept of the observable universe also ties intricately into the theory of cosmic inflation, that breathtakingly rapid expansion the universe underwent in its first fractions of a second after the Big Bang. This swift exponential expansion literally stretched the fabric of space, moving some regions of the universe so incredibly far away from us that their light will perhaps never reach us. This rapid stretching further limits our view, placing even more of the cosmos beyond our observational grasp. It's as if in that first cosmic flash, vast swathes of the universe were whisked away beyond our future ability to see them. This boundary of visibility isn't just about distance. It's also profoundly about time. When we look out into the universe, we are in a very real sense looking back in time. The further we gaze, the older the light we perceive. It's like finding a series of photographs from a very long life. The farther back you look in the album, the younger the subject of the photograph appears. Until finally, we reach the cosmic microwave background radiation, that ancient afterglow of the Big Bang, which represents the earliest light that can be observed. It's the universe's baby picture, showing us what it looked like when it was only about 380,000 years old. Beyond this primordial backdrop, beyond this first photograph, lies an era of the universe that predates starlight, a shadowy period known as the Cosmic Dark Ages. This was a time before any stars had ignited a universe filled only with gas, patiently waiting for the conditions to be just right for the first sparks of light to appear. This era, by its very nature, remains fundamentally hidden from our electromagnetic eyes. So while our instruments grow ever more sensitive and our theories ever more refined, there are fundamental limits to what we can see woven into the very fabric of space-time and the history of the universe itself. These limits are not frustrating barriers, but rather invitations to wonder about the even vaster unseen cosmos and to marvel at the extraordinary journey of the light that does reach us. It's a gentle reminder of the universe's humbling scale and the enduring mysteries that call to us from the cosmic deep. As we venture further into the cosmos, seeking to unveil the mysteries that lie beyond our immediate perception, astronomers employ an arsenal of sophisticated tools to observe distant objects. These instruments, each meticulously designed to capture different aspects of the universe's grand narrative, allow us to peer into the depths of space and time, revealing the cosmos in unprecedented detail. It's like having a set of specialized senses, each one attuned to a different whisper or glimmer from across the cosmic ocean. At the forefront of these observational tools are telescopes, which, as we've noted, come in various forms, each tailored to different wavelengths of light. Imagine them as different kinds of cosmic nets, each designed to catch a particular kind of light particle. Optical telescopes, the grand old sentinels of astronomy, have been the backbone of our cosmic exploration for centuries. These magnificent instruments, ranging from massive ground-based observatories nestled atop remote mountains to the delicate precision of space telescopes, like the Hubble Space Telescope, enable us to observe planets, stars, galaxies, and nebulae in the visible spectrum, the light our eyes are capable of perceiving. They are our direct window into the familiar beauty of the night sky, allowing us to see the sparkling jewels of star clusters and the swirling arms of distant galaxies, just as they might appear if we could somehow fly close enough to them. However, the universe whispers its secrets across a far broader spectrum of light, much of which is utterly invisible to the naked eye. To capture this hidden information, astronomers have developed other equally remarkable cosmic senses. Radio telescopes, for instance, use immense, often dish-shaped antennas, like giant ears, tilted towards the sky to detect radio waves emanating from space. These incredibly long waves are born from phenomena quite different from those that produce visible light. Instruments such as the Very Large Array in New Mexico or the Atacama Large Millimeter, Submillimeter Array ALMA in Chile, can observe the cold, dark regions of the universe, places where visible light is simply absorbed or scattered. They allow us to probe vast gas and dust clouds where new stars are slowly, patiently being born, or to listen to the faint, ancient hum of the remnants of the Big Bang itself. Radio astronomy truly opens a window into the otherwise silent and invisible corners of the cosmos, revealing the gentle stirrings of cosmic creation. Moving to warmer, more shrouded realms, infrared telescopes, like the now retired but still legendary Spitzer Space Telescope, possess a remarkable ability to pierce through cosmic dust clouds. These clouds, dense veils of obscuring particles, would completely hide celestial wonders from optical telescopes. But infrared light, with its longer wavelengths, can often pass right through, revealing hidden star clusters glittering behind the dust, or distant galaxies that were previously concealed. This gives us invaluable insights into the processes of star formation and the conditions of the early universe, allowing us to see nascent worlds taking shape in their cloudy cradles. Conversely, at the very high energy end of the spectrum, X-ray and gamma-ray observatories, including the exquisite Chandra X-ray Observatory and the mighty Fermi Gamma-ray Space Telescope, explore the universe's most energetic and violent phenomena. They study the fierce, searing light emitted from the scorching regions around black holes, the incredibly dense surfaces of neutron stars, and the cataclysmic explosions of supernovae. These high-energy observations uncover the raw power and extreme mechanisms behind these powerful cosmic events, allowing us to glimpse the most dramatic acts in the universe's grand play. Beyond the familiar realms of electromagnetic radiation, recent advancements have introduced entirely new revolutionary tools for astronomical observation, allowing us to perceive the universe in ways previously unimaginable. Gravitational wave detectors such as LIGO Laser Interferometer, Gravitational Wave Observatory, and Virgo have opened a completely new window onto the cosmos. They are not designed to catch light, but rather to detect tiny, almost imperceptible ripples in the very fabric of space-time itself, like the faintest tremors on a cosmic ocean. These ripples are produced by unimaginably powerful cataclysmic events, such as the mergers of black holes or neutron stars. The first detection of gravitational waves in 2015 inaugurated the era of multi-messenger astronomy, a groundbreaking approach where gravitational waves and electromagnetic signals are combined to provide a more complete, richer picture of cosmic events. It's like listening to the sound of a cosmic drumbeat while simultaneously seeing its light, giving us a much deeper understanding. Adding to this suite of new senses are neutrino observatories like the colossal ice cube Neutrino Observatory, located deep within the Antarctic ice. These observatories detect nearly massless particles called neutrinos, which, as we touched upon, are truly the ghosts of the cosmos. Because they interact so weakly with matter, neutrinos can traverse vast cosmic distances, streaming unimpeded through stars and planets, carrying direct clues about their origins. They offer a unique, almost untouched perspective on astrophysical processes, such as the nuclear fusion that powers our sun and the violent explosions of supernovae. It's like being able to hear a conversation happening inside the very heart of a star. And our exploration isn't just about looking outwards from Earth. The pursuit of understanding distant objects in the universe is also propelled by interplanetary missions. Spacecraft and probes like the venerable Voyager probes that have ventured into interstellar space, the New Horizons mission to Pluto, that gave us breathtaking close-ups of that distant dwarf planet, and the intrepid Mars rovers that crawl across the red dusty surface extend our sensory reach. They provide us with up-close observations of planets, moons, and other celestial bodies, not just within our own solar system, but also glimpses of what lies beyond. Each of these tools, whether a colossal telescope or a tiny intrepid rover, plays a critical role in unraveling the mysteries of the cosmos. By combining observations across the entire electromagnetic spectrum with the new vistas opened by gravitational waves and neutrinos, astronomers can construct an ever more comprehensive understanding of the universe's structure, its grand evolution, and the fundamental elegant laws that quietly govern it all. Delving deeper into our cosmic journey, we encounter a natural curiosity about the limits of our observation. It is one thing to know how we observe, but another to understand why there are boundaries to our sight. Why can't we see beyond the observable universe? This question, at its heart, touches on fundamental aspects of physics and the very nature of the universe itself, reminding us that even the most powerful instruments are bound by cosmic rules. As we've gently explored, the observable universe is defined by the farthest reaches from which light has had enough time to travel to us since the universe's inception, approximately 13.8 billion years ago. This boundary, this cosmic shoreline, is not a physical wall in space. Instead, it is a limitation imposed by two unwavering cosmic realities: the finite speed of light and the finite age of the universe. Think of it as a cosmic game of catch. Light is the ball, and it can only travel so fast. The universe is the field, and it has only been around for a certain amount of time, so the ball can only have traveled a certain distance to us in that time. Light travels at a constant speed of about 299,792 kilometers per second in the vacuum of space. This speed, often referred to as c, sets a cosmic speed limit for information and interactions. It dictates the maximum distance from which any information carried by light or any other form of electromagnetic radiation could possibly reach us. Since the universe began its grand unfolding about 13.8 billion years ago, the farthest light we can possibly observe has traveled from a distance that corresponds directly to this age. This allows us to see as far back as the cosmic light horizon, a concept that sounds like a physical barrier, but is in fact a temporal one. This horizon marks the very edge of our observable universe. Due to the universe's continuous expansion since the Big Bang, that edge is currently estimated to be about 46.5 billion light-years away. This is the furthest point in space whose light, having begun its journey towards us from near the dawn of time, has finally arrived. Beyond this horizon lies the unobservable universe. It remains hidden from our view, not because it is empty, or because there is nothing there, but simply because the light from these regions has not yet had enough time to reach us. Imagine shouting across an immense canyon. If your voice hasn't yet reached the other side, it doesn't mean the other side doesn't exist. It just means the sound hasn't traveled that far yet. Similarly, the light from the unobservable universe is still on its cosmic journey, destined to arrive at our cosmic shores in the deep distant future, long after we are gone. Furthermore, the very expansion of the universe driven by the enigmatic dark energy causes distant galaxies to recede from us at speeds that increase with their distance. It's like stretching a rubber band with ants on it. The ants aren't moving on the rubber band, but the rubber band itself is stretching, increasing the distance between them. At a certain point beyond what's known as the Hubble length, this recession speed of distant objects, due to the stretching of space, can actually exceed the speed of light. Now, this doesn't violate Albert Einstein's profound theory of relativity, which famously prohibits objects within space from moving faster than light. The crucial nuance is that it's the fabric of space itself that is expanding, carrying galaxies along with it, rather than the galaxies themselves moving through space faster than light. It's a subtle yet profound distinction that underlines the counterintuitive nature of the cosmos on its grandest scales. The concept of the observable universe also ties into the theory of cosmic inflation, that incredibly rapid exponential expansion that the universe underwent in its first tiny fractions of a second after the Big Bang. This swift, almost instantaneous burst of expansion stretched the very fabric of space so dramatically that it pushed some regions of the universe so incredibly far away, so incredibly fast, that their light will, in all likelihood, never reach us. This rapid early expansion further limits our view, placing even more of the cosmos beyond our current observational reach. It's a reminder of the universe's dynamic and ever-changing nature, a tapestry that is constantly unfurling and evolving over billions of years. This boundary of visibility isn't just about distance, it's also profoundly about time. When we gaze out into the cosmos, we are in a very real sense looking back in time. The further we look, the older the light we perceive, the more ancient the snapshot we are capturing. Imagine you're watching a cosmic film in slow motion. The farther back you rewind, the earlier the scenes you witness. This cosmic film continues to rewind until we reach the cosmic microwave background radiation, that gentle ancient afterglow of the Big Bang, which represents the earliest light that can be observed. It's like the last frame of the earliest part of the film, showing us the universe when it was just a tiny fraction of its current age. Beyond this primordial backdrop lies an era of the universe that predates starlight, a shadowy period known as the Cosmic Dark Ages. This was a time before any stars had ignited a universe filled only with gas, patiently waiting for the conditions to be just right for the first sparks of light to appear. This era, by its very nature, remains fundamentally hidden from our electromagnetic eyes. So while our instruments grow ever more sensitive and our theories ever more refined, there are fundamental limits to what we can see woven into the very fabric of space-time and the history of the universe itself. These limits are not frustrating barriers, but rather invitations to wonder about the even vaster unseen cosmos and to marvel at the extraordinary journey of the light that does reach us. It's a gentle reminder of the universe's humbling scale and the enduring mysteries that call to us from the cosmic deep whispering of realms yet unknown and stories yet untold. As we journey across the cosmic ocean, a breathtaking realization emerges about the universe's grandest architecture, a structure that feels both immense and delicately intricate, the cosmic web. Imagine a vast, luminous spider web stretching across unimaginable distances, its threads woven from galaxies and clusters of galaxies, all connected by invisible bridges of dark matter. This web-like network isn't just a pretty picture. It represents the universe's largest scale structure, the very skeleton upon which everything else is built. It's a direct consequence of the subtle, uneven distribution of matter that emerged from the Big Bang, patiently shaped over billions of years by the relentless, quiet, gravitational pull of dark matter. This vast cosmic tapestry, with its bright threads and gaping voids, tells a fundamental story about how the universe came to be. Understanding the cosmic web begins, as so many cosmic stories do with the early universe, in those first fleeting moments after the Big Bang. In that unimaginably hot and dense primordial soup of particles, tiny, almost imperceptible quantum fluctuations occurred. Think of these as the smallest, most delicate ripples in a cosmic pond, caused by the inherent quantum uncertainty of existence itself. These minute variations in density, these tiny whispers of difference, were the original seeds. As the universe began its rapid expansion and cooling these minute overdensities, the slightly lumpier parts of the cosmic soup began to gently draw in more matter, amplified by the irresistible gravitational attraction of dark matter. Over billions of years, these tiny ripples grew, becoming the gravitational cradles around which gas and dust could gather, eventually condensing and igniting to form the first stars, then the first galaxies, and finally, the colossal galaxy clusters we observe today. Conversely, the regions of slightly lower density in the primordial soup naturally became the cosmic voids we observe today, vast empty spaces that punctuate the fabric of the cosmos like silent lakes between the glowing continents of galaxies. The intricate structure of the cosmic web is profoundly dominated by dark matter. We've talked about dark matter as the cosmic glue, but in the context of the cosmic web, it's more like the invisible scaffolding, the unseen framework that gives the universe its shape. This mysterious substance, invisible to all our senses and all our instruments, constitutes about 27% of the universe's total mass and energy content. We cannot see dark matter directly. It does not emit, absorb, or reflect light, making it a ghost in the cosmic machine. Yet its presence is undeniable, inferred from its profound gravitational effects on visible matter, on the light that travels through the cosmos, and most significantly, on the grand structure of the universe itself. It was dark matter's unwavering gravitational pull that sculpted the cosmic web patiently, drawing ordinary matter into the dense, bright filaments and nodes where galaxies and galaxy clusters reside, and leaving behind the vast, dark voids. Without dark matter, the universe would be a much more uniform, less structured place, lacking the beautiful, intricate patterns we observe. Our ability to actually see and map this invisible cosmic web has been revolutionized by massive galaxy surveys, like those meticulously carried out by the Sloan Digital Sky Survey (SDSS). Imagine mapping every tree in a vast forest, then seeing that the trees are not randomly scattered, but grow in dense groves connected by winding paths with large empty clearings between them. These surveys chart the positions and movements of hundreds of thousands, even millions of galaxies across vast stretches of the universe, revealing the intricate glowing patterns of the cosmic web in stunning detail. What they show us is that galaxies are not randomly distributed throughout space like sprinkles on a cake. Instead, they are gracefully aligned along filaments that span millions of light years, like shimmering cosmic rivers. These filaments surround great voids, and they converge at dense, massive nodes, which are the cosmic cities where galaxy clusters, the largest known structures of galaxies, reside. It's important to remember that the cosmic web is not a static, frozen relic of the past. It is a dynamic, evolving entity, constantly shifting and reshaping itself over cosmic timescales. Galaxies are not fixed in place. They are perpetually in motion, gently moving along these vast filaments, subtly drawn towards the gravitational wells of massive galaxy clusters, like drops of water slowly trickling down a vast invisible net. This ongoing motion, this cosmic flow, reflects the continuous process of structure formation in the universe, a process tirelessly driven by the intricate interplay between the pervasive dark matter and the fundamental force of gravity. It's a slow-motion dance that has been unfolding for billions of years, constantly building and refining the universe's grand design. Studying the cosmic web is crucial for several profound reasons. Firstly, it offers us invaluable insights into the elusive role of dark matter in cosmic evolution. By observing how galaxies cluster and how the web is structured, we can infer the properties and distribution of this invisible substance that makes up the bulk of the universe's mass. Secondly, it sheds light on the very process of galaxy formation and growth. How do these magnificent islands of stars come into being, and how do they grow and evolve over time? The cosmic web provides the environmental context for these processes, showing us how the density and location within the web influence a galaxy's life. Thirdly, it helps us understand the large-scale distribution of matter in the universe, providing a comprehensive map of where everything is and where it's going. Furthermore, understanding the cosmic web is absolutely essential for astronomers to constrain cosmological models. By comparing the observed structure of the web with the predictions of different models, we can refine our understanding of the universe's fundamental parameters, including the nature of dark energy, that mysterious force driving the accelerated expansion of the universe. The web, in its vastness and intricacy, is a key piece of the puzzle, a silent witness to the universe's entire history. Within our universe, so-called superclusters represent some of the largest and most awe-inspiring structures, truly embodying the immense scale and breathtaking complexity of the cosmos. Imagine these not just as single groups of galaxies, but as vast cities of galaxies made up of countless smaller towns, galaxy groups and bustling metropolises, galaxy clusters. These colossal formations are interconnected by the same gossamer filaments of dark matter that form the cosmic web, spanning hundreds of millions of light-years across. The significance of superclusters lies not only in their truly mind-boggling size, but also in what they quietly reveal about the underlying fabric of the universe itself. The subtle, uneven distribution of matter and the powerful yet gentle gravitational forces that relentlessly sculpt the cosmos into its current intricate form. They are cosmic landmarks, signposts in the vast ocean of space. Superclusters are absolutely crucial for understanding the large-scale structure of the universe. They typically form at the intersections of those cosmic web filaments, those vast invisible highways of dark matter that crisscross the universe, shaping the distribution of galaxies and galaxy clusters. This magnificent web-like structure is a direct consequence of the early universe's tiny, almost imperceptible fluctuations. Those initial ripples in the cosmic pond, magnified patiently over billions of years by the steady, persistent gravitational pull of dark matter. By studying superclusters, by mapping their extent and the way galaxies move within them, astronomers can gently trace the evolution of these monumental structures from the earliest stages of the universe. This offers us invaluable insights into the mysterious nature of dark matter itself and the overarching dynamics of cosmic expansion. It's like finding ancient ruins, and by studying their foundations, understanding the principles by which a lost civilization built its grand cities. One of the most famous and humbling examples of these superclusters is the Laniakea supercluster. Its name Laniakea beautifully means immense heaven in Hawaiian, and it is within this very supercluster that our own Milky Way galaxy quietly resides among its tens of thousands of other member galaxies. Spanning an astonishing 500 million light-years, Laniakea's discovery gently underscored the profound interconnectedness of galaxies within the universe, highlighting our own small precious place within these incredibly vast cosmic structures. It's like discovering that our own small town is part of an enormous sprawling metropolitan area. The subtle, majestic flows of galaxies towards denser regions within superclusters, driven by the irresistible silent hand of gravitational attraction, underscore the incredibly dynamic nature of the cosmos. Galaxies are not static points of light. They are constantly moving, interacting, and dancing within this grand evolving framework, drawn by unseen forces toward the centers of these cosmic cities. Superclusters also play a truly pivotal role in cosmology, the grand study of the universe's origin, its immense structure, its slow, patient evolution, and its eventual unknown fate. The intricate distribution and the sheer mass of superclusters profoundly influence the universe's overall geometry and its rate of expansion, which are central to understanding our best cosmological models. Observations of superclusters, carefully mapping their distribution and their gravitational influence, can help astronomers refine their measurements of the universe's expansion rate. This in turn provides crucial evidence for the presence and behavior of dark energy, that mysterious force that is accelerating the expansion of the universe, gently pushing everything further apart. Moreover, superclusters serve as vast natural laboratories for studying galaxy evolution on the largest scales imaginable. The environments within superclusters are incredibly diverse, from the dense, bustling centers of galaxy clusters, where galaxies collide and merge with greater frequency, to the more isolated galaxies residing in their quiet outskirts. These varying environments offer astronomers a rich tapestry of conditions to observe, helping us understand how galaxies change over time, how they grow, how they form new stars, and how their evolution is profoundly influenced by their cosmic surroundings. It's like studying different ecosystems to understand how life adapts and changes. As we continue our gentle journey through the universe's vast structures, we inevitably encounter the concept of voids in space. These aren't just empty patches on a map. They are in their own silent way as crucial as the brightest galaxies in understanding the universe's large-scale structure and its long evolutionary history. Think of them not as holes, but as the negative space in a painting defining the intricate structure by outlining where galaxies are not just as clusters and superclusters tell us where galaxies do congregate. The very existence of these vast, relatively empty regions strongly supports our current theories of cosmic inflation and the precise distribution of dark matter, suggesting that those tiny primordial quantum fluctuations in the early universe gracefully led to the uneven distribution of matter we observe today, sculpting both the bright threads and the empty spaces. Despite their name, voids are not entirely empty, not completely devoid of light and matter. They are more like very sparse regions. They do contain some galaxies, albeit in much lower numbers than the vibrant filaments and clusters. These galaxies found within voids are often smaller, less massive, and tend to be less luminous than their counterparts in denser, more bustling environments, like galaxy clusters. Studying these relatively isolated galaxies is incredibly valuable, because they are largely free from the complex gravitational interactions that dominate the lives of galaxies in crowded settings. They offer a unique, quiet laboratory to gain insights into fundamental processes of galaxy formation and evolution. It's like studying a species in its natural undisturbed habitat, rather than in a busy city. The discovery and meticulous mapping of these cosmic voids have been made possible by those large-scale galaxy surveys we discussed, which painstakingly chart the precise positions of galaxies across the vast three-dimensional sky. These surveys beautifully reveal the cosmic web's filamentous structure and the immense voids that gently separate these filaments. The size and shape of voids can vary greatly. The largest known void in the universe, the majestic Bode's void, stretches approximately 330 million light-years across a truly silent and immense emptiness. These voids are not static. Like everything else in the universe, they are evolving over time, subtly expanding as the universe itself expands, driven by dark energy's gentle repulsive force. The study of voids also contributes significantly to cosmology, offering a unique vantage point for understanding the universe's grand expansion and the mysterious nature of dark energy. Since voids, despite their emptiness, occupy most of the universe's volume, their dynamics and evolution are absolutely essential for constructing a complete, accurate picture of cosmic history. Additionally, the distribution and size of voids can be used as powerful tools to test our models of the universe, providing precise constraints on the properties of both dark matter and dark energy. It's like using the empty spaces in a complex puzzle to verify the shape and fit of the pieces you already have. The voids in their quiet immensity are key silent witnesses to the universe's ongoing story, revealing as much about what is there by showing us what is not. As we continue our journey through the cosmic web, our gaze is inevitably drawn to the most profound and enigmatic knots within its vast structure, black holes. These mysterious entities exist at the crossroads of astrophysics and theoretical physics, where the known laws of gravity are stretched to their absolute limits, and where even light itself cannot escape their overwhelming pull. They are not merely cosmic oddities. Rather, they are integral to the very structure and evolution of the universe. Imagine them not just as bottomless pits, but as profound gravitational anchors, playing a pivotal, often unseen role in the cosmic ballet influencing the formation of galaxies, the birth and death of stars, and possibly even the intricate distribution of matter across the cosmic web. The fascination with black holes lies not only in their mysterious, awe-inspiring nature, but also in their significant pervasive impact on the cosmos at large. They are silent conductors of a grand cosmic orchestra, their presence shaping the music of the universe. At the very heart of most, if not all, large galaxies, including our own spiral home, the Milky Way, resides a colossal entity, a supermassive black hole. These cosmic giants are truly immense, weighing in at millions to even billions of times the mass of our humble sun. They are not just passive remnants of the universe's violent past. Instead, they are active players, dynamic gravitational engines that exert a profound influence on their host galaxies. Think of them as the quiet, immensely powerful hearts of these galactic cities. They are believed to play a critical role in regulating star formation, gently stirring the gas and dust in their galactic neighborhoods, sometimes triggering bursts of new stars, and at other times, suppressing star birth. They also drive the evolution of galaxies through their energetic outputs, sending out powerful jets of particles and radiation that can shape the surrounding interstellar medium. As galaxies slowly gracefully merge, a common occurrence in the dynamic cosmos, their central black holes are also drawn towards each other. They will gradually spiral inward, a slow-motion cosmic dance, until they finally merge to form an even more massive black hole, releasing vast amounts of energy in the process and reshaping the gravitational landscape of the newly formed galaxy. Black holes also contribute significantly to the architecture of the cosmic web by powering some of the universe's most luminous objects, quasars, and active galactic nuclei, AGN. A quasar, in essence, is a supermassive black hole at the center of a galaxy that is actively feeding furiously, drawing in vast quantities of gas and dust. As this matter spirals inward, it heats up to incredible temperatures, emitting blinding amounts of light and radiation, often outshining all the stars in its host galaxy combined. These intensely luminous beacons, visible across unimaginably vast cosmic distances, serve as cosmic lighthouses, gently illuminating the intergalactic medium and affecting the formation and evolution of galaxies along the cosmic web's intricate filaments. The feedback mechanisms from these active galactic nuclei, where energy is injected back into the surrounding gas, can sometimes halt star formation in galaxies, influencing the large-scale structure of the universe by sweeping away the very gas that would otherwise coalesce into new stars. They are like quiet, powerful engines, subtly directing the cosmic currents. Furthermore, the incredible gravitational waves produced by merging black holes, first detected with such profound significance in 2015, have opened an entirely new window onto the universe. These are not light waves, but ripples in the very fabric of space-time itself, generated by the most cataclysmic and energetic events in the cosmos. Imagine dropping a stone into a still pond. The ripples spread outwards. Now imagine two massive cosmic stones like black holes colliding and merging. The ripples they create are gravitational waves, and they carry information about these extreme events directly to us. These waves provide a novel way to probe the universe's structure, offering unprecedented insights into the hidden population of black holes and their profound role in cosmic evolution. Gravitational wave astronomy could in time shed crucial light on the precise distribution of black holes throughout the cosmic web, further elucidating their quiet yet powerful contribution to the universe's grand architecture. It's like having a new sense, allowing us to feel the subtle tremors of the universe's most dramatic events. The study of black holes also intersects with the most fundamental questions about the nature of the universe and reality itself. These extreme gravitational environments are perfect testing grounds for theories that attempt to reconcile the two great pillars of modern physics: quantum mechanics, which governs the subatomic world, and general relativity, which describes gravity and the large-scale structure of the cosmos. Theories such as string theory and loop quantum gravity often consider black holes as crucial laboratories for testing new ideas about the very nature of space-time, the true essence of gravity, and the universe's ultimate fate. One of the most compelling puzzles, the information paradox, which questions how information is preserved in a universe that contains black holes that seem to destroy everything, potentially holds keys to understanding the universe's most fundamental laws. It's a deep, quiet mystery that beckons physicists to venture into the unknown. Black holes are far more than just exotic cosmic oddities. They are central to the very structure and profound dynamics of the universe. From anchoring the galaxies holding them together with their immense gravity, to subtly influencing the cosmic web, and even offering tantalizing clues to the fundamental forces of nature. Black holes are pivotal in our quiet quest to understand the cosmos. Their study not only challenges our deepest conceptions of space and time, bending and warping them in unimaginable ways, but also highlights the intrinsic interconnectedness of all cosmic phenomena, from the smallest ephemeral particles that flicker into existence to the largest, most magnificent structures in the universe. They are a constant reminder that the universe holds depths of wonder that we are only just beginning to fathom. On the topic of these vast structures and the threads of the cosmic web, let's gently turn our attention to the spacious, quiet realms known as voids in space. These are not just areas of nothingness, of utter emptiness. Instead, they are key to understanding the universe's large-scale structure and its long evolutionary history. Think of them like the negative space in a grand painting. They define the structure by outlining where the galaxies are not just as the vibrant clusters and superclusters tell us where galaxies brightly congregate. The very existence of these vast underdense regions provides strong support for our theories of cosmic inflation and the precise distribution of dark matter, suggesting that the tiny, almost imperceptible quantum fluctuations in the early universe gently led to the uneven distribution of matter we observe today, sculpting both the bright dense threads and the quiet empty spaces between them. Despite their name, these voids are not entirely empty. They are more like very sparse, quiet neighborhoods. They do contain some galaxies, albeit in much lower numbers and spread far more thinly than in the bustling cosmic cities. These galaxies found within voids are often smaller, less massive, and less luminous than their counterparts that reside in denser environments like galaxy clusters. Studying these isolated galaxies can provide invaluable insights into the fundamental processes of galaxy formation and evolution, precisely because they are relatively free from the complex gravitational interactions and chaotic mergers that are so prevalent in more crowded settings. It's like studying a delicate flower that has grown in a serene, untouched meadow, allowing us to understand its natural development without the interference of a bustling garden. The discovery and meticulous mapping of these cosmic voids have been made possible by those grand, large-scale galaxy surveys we discussed earlier. These surveys painstakingly chart the precise positions of millions of galaxies across the sky, revealing the cosmic web's intricate, filamentous structure and the vast, silent voids that gently separate these luminous threads. The size and shape of voids can vary greatly from smaller bubble-like regions to truly immense expanses. For instance, the largest known void in the universe, the majestic Bode's void, stretches approximately 330 million light-years across a truly silent and immense emptiness in the cosmic fabric. These voids are not static features frozen in time. Like everything else in the universe, they evolve over time, quietly expanding as the universe itself expands, driven by dark energy's subtle repulsive force. They are a testament to the dynamic, ever-changing nature of the cosmos. The study of voids also contributes significantly to cosmology, offering a unique vantage point for understanding the universe's grand expansion and the mysterious nature of dark energy. Since voids, despite their apparent emptiness, actually occupy most of the universe's volume, their dynamics and evolution are absolutely essential for constructing a complete, accurate picture of cosmic history. Their gentle expansion provides a direct measure of dark energy's influence. Additionally, the distribution and sheer size of voids can be used as powerful tools to test and refine our cosmological models, providing crucial constraints on the enigmatic properties of both dark matter and dark energy. It's like using the empty spaces in a complex puzzle to verify the shape and fit of the pieces you already have. The voids in their quiet immensity are key silent witnesses to the universe's ongoing story, revealing as much about what is there by showing us what is not. As we approach the heart of our cosmic mystery, we must now turn our attention to the two most enigmatic components of the universe, those silent, unseen forces that shape its destiny and constitute its vast majority, dark matter and dark energy. Despite their similar names suggesting some hidden kinship, they are fundamentally distinct components of the universe, each playing a unique, profound role. Imagine them as the two sides of a hidden coin, one drawing things together, the other gently pushing them apart. Unraveling their secrets is like trying to understand the quiet, powerful currents beneath the surface of a vast ocean currents that determine its ebb and flow. Let's begin by returning to dark matter, an enigmatic substance that, despite being utterly invisible and undetectable by conventional means, makes up about 27% of the universe. Unlike the ordinary matter that forms the stars, the planets, the very dust motes in the air, and indeed ourselves, everything we can see, touch, or measure, dark matter does not emit, absorb, or reflect light. It passes through us and through our instruments like a ghost. This makes it profoundly difficult to observe directly a true whisper in the cosmic wind. Its presence, however, is inferred, its influence felt through its unwavering gravitational effects on visible matter, on the light that journeys across the cosmos, and on the grand sprawling structure of the universe itself. It's like watching a group of dancers moving in a circle and realizing that they are orbiting around something you cannot see, but whose invisible pull is undeniably there, guiding their every step. The story of dark matter's quiet unveiling begins with the patient observations of galaxies and galaxy clusters. Back in the 1930s, a keen-eyed astronomer named Fritz Zwicky was studying the Coma galaxy cluster. He noticed something peculiar. The galaxies within the cluster were moving at such incredibly high velocities that if only the visible matter were at play, they should have simply flown apart, scattering into the vastness of space like dandelion seeds in a strong breeze. There simply wasn't enough visible gravity to hold them together. This startling discrepancy, this quiet puzzle, suggested the presence of a significant amount of unseen matter, a hidden mass exerting a powerful gravitational pull. Zwicky, with a stroke of quiet brilliance, termed this unseen influence dark matter, or Dunkel Materie, in his native German. Further compelling evidence for dark matter came from the meticulous work of Vera Rubin and her colleagues in the 1970s. They were studying the rotation curves of galaxies. Imagine a merry-go-round. Near the center, the horses move slowly, but as you move to the edge, they whiz by at much higher speeds. You'd expect a similar pattern in galaxies. Stars near the center, where most of the visible mass is concentrated, should orbit faster, while stars on the outskirts should move more slowly, experiencing less gravitational pull. However, Rubin's observations revealed something quite different. Stars in the outer regions of galaxies were orbiting at roughly the same speed as those closer to the center. This was a profound cosmic riddle. It strongly implied the presence of a significant amount of unseen mass distributed throughout the galaxy's halo, providing the extra gravitational force necessary to ensure these high orbital speeds at greater distances. This unseen mass, this gentle yet powerful gravitational presence, could not be explained by visible matter alone. It was another undeniable fingerprint of dark matter shaping the graceful whirl of galaxies. Dark matter, though silent and invisible, plays an absolutely crucial foundational role in the formation and evolution of cosmic structures. Imagine trying to build a magnificent skyscraper without any internal steel framework. It would simply collapse. Theories of cosmic evolution suggest that dark matter's pervasive gravitational pull was the very force that initiated the coalescence of gas and dust in the early universe, gently pulling it together into denser regions. These denser regions then became the gravitational cradles, the nurseries that led to the formation of the first stars, and ultimately the magnificent galaxies we observe today. Without dark matter's silent gravitational scaffolding, the dispersed gas in the early universe would not have condensed sufficiently. The universe would be a much more uniform, less structured place, and life as we know it, with its intricate biological forms, simply might not exist. It is the unseen architect of the cosmos building the framework for everything we cherish. Despite its pivotal role in the cosmos, dark matter remains one of the greatest enduring mysteries in science. Its very nature is elusive, like trying to grasp smoke. It does not interact with electromagnetic forces, which means it doesn't emit, absorb, or reflect light, rendering it perfectly invisible and detectable only through its quiet, powerful gravitational effects. Scientists across the globe are engaged in a quiet, relentless search for dark matter particles directly. They are building exquisitely sensitive detectors, often buried deep underground in old mine shafts, to shield them from cosmic rays and other background noise, patiently waiting for the faintest, rarest interaction. The hope is that one day a dark matter particle might gently bump into one of their detector atoms, revealing its secret. The nature of dark matter is a subject of intense research and thoughtful speculation. Several candidate particles have been proposed, each a whisper of a possibility. Weakly interacting, massive particles. WIMPs, tiny axions, or elusive sterile neutrinos. But as of yet, none have been definitively detected. The search for dark matter is not just a quest to understand what this unseen substance is. It is a profound journey that gently challenges our understanding of fundamental physics of the universe itself and of the very nature of matter. In this exploration of dark matter, we confront the limits of our current knowledge and technological capabilities, embarking on a quest that beautifully bridges the worlds of the very large, the immense cosmos, and the very small, the realm of particle physics. Unraveling the mystery of dark matter is not only about discovering what makes up most of the universe's mass, but also about deepening our understanding of the fundamental elegant laws that quietly govern the cosmos, offering tantalizing insights into the very nature of space-time and reality itself. Dark matter, while invisible and elusive, leaves a series of profound cosmic fingerprints that have allowed scientists to deduce its pervasive presence and understand its fundamental quiet role in shaping the structure and dynamics of the cosmos. These aren't just theoretical musings. They are observations carefully gathered that point to its undeniable influence. The journey to understanding dark matter's existence, as we mentioned, began with the keen observation of galaxy clusters. In the 1930s, Fritz Zwicky noticed that galaxies within the Coma cluster were moving at velocities so high that the gravitational force from their visible mass alone was insufficient to prevent them from scattering into the vastness of space. This quiet discrepancy, this subtle imbalance, strongly suggested the presence of a substantial amount of unseen mass, a silent, powerful hand guiding the galactic dance. Further compelling evidence for dark matter came from the meticulous study of the rotation curves of galaxies. Imagine a beautiful spiraling galaxy gracefully turning like a cosmic pinwheel. According to our familiar laws of gravity, stars on the outskirts of a galaxy being farther from the bulk of the visible mass, concentrated near the center, should orbit more slowly. But what Vera Rubin and her colleagues observed in the 1970s was truly remarkable. Stars in the outer regions of galaxies were orbiting at roughly the same speed as those closer to the center. This phenomenon defied explanation by visible matter alone. It quietly yet powerfully implied the presence of a significant amount of unseen mass extending far beyond the visible spiral, providing the additional gravitational force needed to ensure these high orbital speeds at greater distances. This mass, this invisible presence, holds galaxies together, preventing them from simply tearing apart as they spin. It's like a hidden anchor, keeping the galactic ship from drifting away. The cosmic microwave background, CMB radiation, that ancient whisper, the afterglow of the Big Bang, provides another crucial piece of evidence for dark matter's pervasive influence. Imagine this radiation as the universe's baby picture, showing us what it looked like when it was only about 380,000 years old. Detailed measurements of the CMB by satellites like COBE-WMAP and the Planck Space Observatory have revealed tiny, subtle fluctuations in temperature. These fluctuations, like faint ripples on the surface of that cosmic baby picture, are indicative of the subtle density variations that existed in the very early universe. The specific distribution and scale of these fluctuations precisely match predictions from cosmological models that include dark matter. This strongly suggests that dark matter was absolutely instrumental in the formation of the universe's large-scale structure, providing the gravitational seeds for galaxies and clusters to form. Without dark matter, those early ripples would not have grown into the grand structures we see today. Finally, gravitational lensing offers perhaps the most visually compelling evidence for dark matter. This phenomenon occurs when the immense gravitational field of a massive object, be it a galaxy or a galaxy cluster, bends and distorts the path of light coming from a more distant object behind it. It's like looking through a warped glass pane. Observations of gravitational lensing, where the bending of light is far too pronounced to be accounted for by visible matter alone, unmistakably indicate the presence of massive invisible structures. These structures, with their powerful gravitational influence, can only be attributed to dark matter. Gravitational lensing acts as a natural cosmic magnifying glass, not only confirming dark matter's presence, but also allowing astronomers to actually map its distribution in the universe, revealing its hidden contours. Together, these diverse observations, from the quiet dance of galaxies to the faint echoes of the Big Bang and the warped paths of distant light, form a compelling, undeniable body of evidence for dark matter's profound existence and its quiet, pervasive role in shaping the cosmos. The role of dark matter in the universe can be beautifully likened to the invisible framework of a building, essential for holding the grand structure together, even though you cannot see it. One of its primary and most crucial roles is in the formation of galaxies and galaxy clusters. In the very early universe, the gentle, pervasive gravitational pull of dark matter initiated the slow, patient coalescence of ordinary gas and dust. Without dark matter's invisible gravitational scaffolding, the dispersed gas in the early universe would not have condensed sufficiently to form the first stars, the myriad planets, and the magnificent galaxies we observe today. The universe would have remained a much more diffuse, less interesting place. Moreover, dark matter is absolutely critical in explaining the puzzling rotation curves of galaxies. As we discussed, observations show that stars at the very edges of galaxies rotate at similar speeds to those nearer the center. This phenomenon defies the expectations based solely on the visible mass of galaxies. Dark matter provides the additional invisible gravitational force needed to explain these remarkably uniform rotation speeds, effectively holding galaxies together and preventing them from tearing apart as they spin with such surprising velocity. It's the silent, unseen hand that keeps the galactic whirl intact. At larger scales, dark matter profoundly influences the overall structure of the universe, forming what we gently refer to as the cosmic web. This vast, intricate network of galaxies and galaxy clusters, connected by subtle filaments of dark matter and separated by immense voids, forms the very backbone of the cosmos. Dark matter's gravitational effects are directly responsible for the clustering and precise distribution of galaxies, shaping them into the intricate, beautiful patterns observed by astronomers. Without dark matter, the cosmic web's delicate gossamer structure with its luminous filaments and its massive nodes where galaxies cluster like cosmic cities simply would not exist. It is the unseen architect of the universe's grand design. Finally, dark matter also plays a vital role in gravitational lensing, a phenomenon where the path of light from a distant galaxy or quasar is bent and distorted by the gravity of a foreground mass, such as a galaxy cluster. This effect, as we noted, not only confirms the presence of dark matter, but also allows astronomers to meticulously map its distribution throughout the universe. Gravitational lensing acts as a natural cosmic telescope, gently magnifying and distorting the light from distant objects, providing a unique, invaluable tool for probing the unseen dark universe. All these cosmic fingerprints together paint a compelling picture of dark matter as an essential, pervasive, yet still profoundly mysterious component of our universe. Now let us turn our attention to the other side of this mysterious cosmic coin, to dark energy. While dark matter is a gravitational glue, dark energy is a force that seems to push a quiet, persistent pressure that is accelerating the universe's grand expansion. The very concept of dark energy emerged from one of the most surprising and profound observations in modern astronomy, the study of distant supernovae. In the late 1990s, two independent research teams were meticulously observing these incredibly bright exploding stars, which serve as cosmic lighthouses, their consistent brightness allowing astronomers to measure vast cosmic distances. What they found was truly astonishing. These distant supernovae were fainter than expected. This faintness was a crucial clue suggesting that they were actually farther away than scientists had predicted, based on previous models of a universe whose expansion was slowing down under the influence of gravity. This unexpected faintness pointed to a startling revelation: the universe's expansion rate was not slowing down as previously thought, but was in fact accelerating. It was as if a cosmic brake had not only been released, but replaced by a quiet, constant accelerator. This observed acceleration could only be explained by the presence of an unknown energy component with a powerful repulsive force, a force strong enough to overcome gravity's universal pull and actively drive galaxies apart at an ever-increasing speed. This mysterious component, this unseen cosmic accelerator, was given the evocative name dark energy. It was a discovery that profoundly reshaped our understanding of cosmology and the universe's ultimate fate. The precise nature of dark energy remains one of the most profound and alluring mysteries in all of science. Unlike dark matter, which clusters and helps build structures like galaxies and galaxy clusters, dark energy appears to have a uniform presence throughout space, exerting the same gentle repulsive force everywhere. It doesn't seem to dilute as the universe expands. Its density remains constant, a property that sharply distinguishes it from ordinary matter and even dark matter. Imagine filling a balloon with dots as we did before, but now the very rubber of the balloon itself contains a hidden expansive energy that makes it inflate faster and faster, regardless of how thin it gets. One leading theory, a compelling whisper in the scientific community, suggests that dark energy might simply be an intrinsic property of space itself. This idea beautifully described by Albert Einstein's cosmological constant, a term he famously introduced into his equations of general relativity, and later in a moment of humility called his biggest blunder when he thought the universe was static, posits that empty space is not truly empty. Instead, it possesses its own intrinsic energy, a fundamental pressure that gently pushes the universe apart. In this view, the vacuum of space is not a void, but a vibrant, energetic entity. Another possibility, a more dynamic and evolving idea, is that dark energy is a dynamic field somewhat similar to electromagnetic fields, but with a unique repulsive property. This hypothetical field, sometimes gently called quintessence, could change its strength and influence over time, unlike the cosmological constant, which remains eternally constant. Theoretical models propose various forms and behaviors for this quintessence, but as of yet, there is no direct observational evidence to support these more speculative theories. The quest to understand dark energy is a profound journey into the very foundations of physics, asking questions about the very nature of reality itself and what forces truly govern the grand cosmic dance. As we delve into the enigmatic nature of dark energy, we uncover its pivotal, relentless role in the expansion of the universe, a force that accelerates the cosmos's growth far beyond what was once imagined. Dark energy, making up about 68% of the universe's total energy content, acts as a powerful counterbalance to gravity, that familiar force that gently pulls galaxies and other cosmic structures together. But instead of attracting dark energy, repels subtly yet powerfully, pushing the universe's very fabric apart and causing its expansion to accelerate. Imagine a vast cosmic breath being drawn, but instead of slowing down, the inhalation simply gets faster and faster. This cosmic acceleration was first observed in the late 1990s through those meticulous studies of distant supernovae, those cosmic lighthouses we spoke of. Astronomers, with their patient gaze, initially expected these cosmic explosions to show that the universe's expansion was steadily slowing down under the pervasive influence of gravity. It was a reasonable assumption, like expecting a ball thrown into the air to eventually slow its ascent and fall back down. However, the data, those quiet whispers from the distant past, revealed just the opposite. The universe was expanding faster than in the past, a truly startling revelation that pointed directly to the pervasive and profound influence of dark energy. It was as if that thrown ball, instead of slowing, suddenly began to accelerate upwards with an unseen force. Unlike matter, which can cluster and gracefully create structures such as galaxies and galaxy clusters, dark energy is remarkably evenly distributed throughout the universe, like a subtle, pervasive pressure that exists everywhere at once. It exerts the same repulsive force everywhere, leading to an inexorable increase in the rate of expansion over time. The effects of dark energy on the universe's expansion are profound and far-reaching, dictating nothing less than the ultimate fate of the cosmos. If its strength remains constant, or even more dramatically increases over time, the universe could continue expanding indefinitely, growing colder and emptier as galaxies recede further and further apart. In this chilling scenario, often called the Big Freeze or heat death, the universe would eventually reach a state of maximum entropy where all significant energy exchanges would cease, marking the quiet final end of all astronomical processes and perhaps the universe itself. Imagine a cosmic light slowly fading until all that remains is a uniform dark and still emptiness. In more speculative and extreme models, if dark energy were to grow significantly stronger, it could lead to a terrifying Big Rip scenario. In this dramatic possibility, the repulsive force would become so overwhelmingly dominant that it would literally tear apart galaxies, then stars, then planets, and eventually the very atoms themselves, leading to a universe where no structures, not even the smallest particles, could possibly exist. Understanding how dark energy affects the expansion of the universe is not only a matter of meticulously measuring the precise rate of this expansion, but also involves patiently piecing together the entire history of the cosmos. Observations of the cosmic microwave background radiation, that ancient gentle afterglow of the Big Bang, along with vast, painstaking, large-scale surveys of galaxies, provide us with a detailed unfolding map of the universe's evolution. These invaluable data allow scientists to trace the subtle yet powerful influence of dark energy back through billions of years of cosmic history, observing how its repulsive force has slowly, inexorably shaped the cosmos into the grand expanding structure we see today. The study of dark energy and its profound impact on cosmic expansion is at the very forefront of modern cosmology, pushing the boundaries of our understanding. It gently challenges our current understanding of physics, quietly urging us to develop new theories that can explain its mysterious properties and effects. Theories such as quintessence, for instance, propose that dark energy is not a constant, unchanging force, but rather a dynamic field that can subtly change over time, which could in turn have varying and complex effects on the expansion of the universe. The quiet pursuit of dark energy's true nature is a profound journey, one that promises to unlock even deeper secrets about the fundamental workings of the cosmos. Now let us turn our gaze to the very beginning, to that singular monumental moment that marks the origin of the universe as we know it, the Big Bang. Far from being a noisy explosion in space, the Big Bang was the dramatic, rapid expansion of space itself, setting the stage for the cosmos to evolve from an unimaginably hot, incredibly dense state to the vast, cooler expanse filled with galaxies, stars, planets, and perhaps even life that we observe today. Imagine, if you can, all of existence compressed into a space smaller than a single atom. And then, in an instant, that space begins to unfurl, stretch, and expand at an astonishing rate. The Big Bang Theory is not merely a wild speculation. It is a meticulously constructed scientific framework supported by multiple converging lines of evidence, making it the leading, most widely accepted explanation for the universe's origin. One of the most compelling and poetic pieces of evidence is the cosmic microwave background, CMB radiation, a faint, pervasive glow that literally permeates every corner of the universe. This gentle ancient light was discovered almost accidentally in 1965 by Arno Penzias and Robert Wilson, two engineers who were puzzling over a persistent, annoying noise in their radio antenna. That noise turned out to be the universe's most ancient whisper. This discovery provided a direct, unmistakable snapshot of the infant universe, a relic of radiation from about 380,000 years after the Big Bang, when the cosmos finally cooled enough for photons, light particles, to travel freely through space for the first time. The remarkable uniformity of the CMB radiation, combined with its tiny, subtle variations, beautifully matches the predictions from the Big Bang theory, offering us a clear window into the conditions of the early universe. It's like finding a perfectly preserved baby photo of the entire cosmos. Another fundamental pillar supporting the Big Bang theory is the powerful observation of the universe's expansion. As we discussed, Edwin Hubble's observations in the 1920s of distant galaxies moving away from each other unveiled the profound truth that the universe is not static and unchanging, but rather dynamically expanding. This expansion, when gracefully traced backward in time, logically implies that the universe must have originated from a singularly small, incredibly dense point. The Big Bang theory provides the elegant explanation for this observed expansion and accurately predicts that the farther away a galaxy is, the faster it is receding from us, a relationship famously known as Hubble's law, which has been consistently confirmed by countless subsequent observations. It's like watching a film in reverse, tracing the outward motion of cosmic objects back to a single common starting point. The theory also beautifully and successfully accounts for the observed abundance of light elements in the universe, such as hydrogen, helium, and a tiny amount of lithium. Scientists believe that specific nuclear reactions occurring in the first few precious minutes after the Big Bang, during an epoch called Big Bang nucleosynthesis, produced these light elements in proportions that closely match those observed in the universe today. This delicate primordial nucleosynthesis, the process of forming new atomic nuclei from pre-existing matter, provides a crucial independent test for the Big Bang theory, further cementing its status as the cornerstone of modern cosmology. It's like finding the fundamental ingredients of a cosmic recipe perfectly matched to what we see in the vast cosmic kitchen. Despite its immense success and the overwhelming evidence supporting it, the Big Bang theory also gently opens up new questions and profound mysteries, whispering to us of realms yet unknown. These include the very nature of dark matter and dark energy, which, as we've explored, seem to overwhelmingly dominate the universe's mass energy content. What are they truly? And perhaps the most elusive question of all, what preceded the Big Bang? What, if anything, triggered this monumental expansion? The theory, by its very nature, describes the evolution of the universe from that initial hot, dense state, but it does not at present explain what caused that state or what might have existed before it. This leaves a beautiful open space for further theoretical developments and future discoveries, a vast realm for our gentle curiosity to explore. The Big Bang is a powerful beginning to our story, but it is not the whole story. From the pivotal singular moment of the Big Bang, the universe embarked on an unimaginably complex and majestic journey of evolution. It was a gradual, patient transformation, transitioning from that unimaginably hot, dense state to the vast, structured cosmos filled with galaxies, stars, and planets that we observe today. This grand evolution is a sweeping narrative of cosmic expansion, of slow, patient cooling, and of gravity's relentless, quiet work, diligently knitting together the very fabric of the universe over billions upon billions of years. It's a cosmic saga unfolding in slow motion before our very eyes. In the immediate aftermath of the Big Bang, in those first fleeting moments, The universe was an incredibly hot, turbulent cauldron of particles and radiation, a dense, fiery plasma. It was simply too hot and too dense for even atoms to form, much like trying to hold water vapor together in a superheated oven. During this epoch known as the Planck era, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were believed to have been unified, existing as a single indivisible force. As the universe continued its incredibly rapid expansion, it cooled dramatically and quickly, allowing these fundamental forces to separate like threads, unraveling from a tightly wound ball. Then the first fundamental subatomic particles, protons, neutrons, and electrons, began to emerge from the fiery primordial soup. Approximately 380,000 years after the Big Bang, a crucial milestone was reached. The universe had cooled enough to a temperature where electrons previously too energetic to settle could finally combine with protons to form stable, neutral hydrogen atoms. This profound process is known as recombination. This era marked the universe's dramatic transition from being opaque like a thick glowing fog to becoming transparent to light. For the first time, photons, the particles of light, were able to travel freely, unimpeded through space, creating that faint ancient glow we call the cosmic microwave background radiation. This CMB is literally a snapshot of the infant universe, a precious photograph from a time when it was only about 380,000 years old. For the next several hundred million years, the universe entered a quieter, dimmer period, affectionately known as the Cosmic Dark Ages. This was a time before the first stars had ignited a universe filled primarily with neutral hydrogen gas, patiently waiting in the cosmic darkness. But even in this quiet period, gravity, that tireless sculptor, was already at work. It began to gently pull together the first subtle clouds of gas and crucially dark matter, forming the initial seeds of what would become future galaxies. These tiny dense pockets of matter were the gravitational nurseries for the first cosmic lights. The end of the Dark Ages, that period of cosmic waiting, came with the spectacular formation of the first stars. Imagine the universe for so long dark suddenly beginning to flicker with countless points of brilliant light. These first generations of stars were truly immense, burning incredibly brightly and living short, intense lives like cosmic fireworks. When they reached the end of their lives, they died in spectacular, violent supernovae explosions. These explosions were not just dramatic, they were essential for life itself. They acted as cosmic alchemists, forging and then scattering the heavier elements like carbon, oxygen, and iron back into the surrounding space. These heavier elements, the very building blocks of planets and life as we know it, were crucial ingredients for the subsequent generations of stars and worlds. Following the birth of these first stars, galaxies began to truly take shape, forming from the gentle gravitational collapse of those dark matter halos that slowly drew in more gas and dust. Inside these fledgling galaxies, new generations of stars were born, their fiery births, surrounded by swirling disks of material that gradually coalesced into planets, asteroids, and comets. Over vast stretches of cosmic time, galaxies grew larger and more complex through a cosmic dance of mergers and accretions, colliding and combining, to create the diverse range of galactic structures, from elegant spirals to grand ellipticals that we see today. It's a slow-motion ballet of cosmic construction. As the universe continued its grand expansion and gentle cooling, the overall rate of star formation eventually slowed, leading to the current epoch where the formation of new stars is now balanced by the quiet, graceful death of old ones. The recent profound discovery of dark energy, that mysterious force that is accelerating the expansion of the universe, adds another layer of complexity to our understanding of cosmic evolution. It suggests a future in which galaxies will become increasingly isolated from one another, drifting further and further apart, like ships losing sight of each other on an ever-expanding ocean. Today, the universe is a vast, intricate web of galaxies, each a magnificent island universe of its own, separated by immense voids and connected by invisible filaments of dark matter. This intricate structure, from the smallest planetary systems to the largest galactic clusters, is the beautiful, awe-inspiring result of nearly 14 billion years of continuous cosmic evolution, a testament to the quiet power of physical laws to shape the universe from the simplicity of the Big Bang to the complex living tapestry we observe now. Having journeyed through the universe's birth and its long patient evolution, our thoughts naturally drift towards its eventual conclusion. The fate of the universe is a subject of intense scientific inquiry and profound speculation, a cosmic narrative still being written, intertwined with the laws of physics as we understand them, and crucially, with the properties of those silent, pervasive components. Dark matter, dark energy, and the fundamental forces of nature. The ultimate destiny of the cosmos largely hinges on the characteristics and behavior of dark energy, that mysterious force we've explored, which continues to drive the acceleration of the universe's expansion. It is the quiet, persistent architect of our cosmic future. If dark energy continues to dominate the cosmic landscape, as our current observations strongly suggest, then the universe will continue its inexorable expansion at an accelerating rate. Imagine our cosmic balloon inflating faster and faster with no end in sight. In this scenario, galaxies outside our local group, our own Milky Way and its nearest galactic neighbors, will recede from us faster and faster, eventually disappearing beyond our cosmic horizon. This means they will become effectively invisible to us, their light simply unable to reach us, due to the combined effect of their recession speed and the finite speed of light. The universe in this long quiet future would become increasingly cold and empty, growing thinner and more dilute as everything moves further apart. This path leads to a state known as the Big Freeze or heat death, a gentle fading where the universe reaches maximum entropy. All significant energy exchanges would cease, like a clock slowly winding down, marking the quiet final end of all astronomical processes, and potentially the universe itself settling into a state of ultimate stillness. Another possibility, though, one that is far less supported by current observations, is a dramatic reversal known as the Big Crunch. If for some reason dark energy were to weaken over immense stretches of time, or if the universe were to contain enough hidden matter, perhaps far more than we currently estimate, then gravity's pull could eventually overcome dark energy's push. In this scenario, the expansion of the universe would slowly, gently reverse. All matter and space would eventually begin to collapse back inward, drawing closer and closer, eventually spiraling back into an incredibly hot, dense singularity, perhaps similar to the state from which it began. This could theoretically lead to another Big Bang, creating a fascinating cyclic universe model, a cosmic breath perpetually inhaling and exhaling. However, the overwhelming evidence for the currently accelerating expansion of the universe makes the Big Crunch a far less likely outcome based on our present understanding. A more speculative and perhaps more unsettling outcome is the Big Rip, a dramatic possibility contingent on a particular more aggressive form of dark energy. In this scenario, dark energy's repulsive force would not only continue to accelerate the expansion, but would actually grow stronger over time. Imagine the cosmic balloon not just inflating, but the very fabric of the rubber itself becoming thinner and weaker until it can no longer hold together. The repulsive force of dark energy would become so overwhelmingly dominant that it would begin to literally tear apart structures. First galaxy clusters, then individual galaxies, then stars and planets, and eventually, if the force became strong enough, the very atoms themselves. This would lead to a universe where no structures, not even the most fundamental particles, could remain intact, a truly desolate and fragmented end. Beyond these grand cosmological scenarios, the future of individual cosmic entities, stars, galaxies, and black holes plays out on similarly vast timescales. Stars will continue to form for trillions of years as long as there are sufficient reservoirs of gas in galaxies. But eventually, this cosmic fuel will be depleted or expelled into the void. Existing stars, having patiently burned their nuclear fuel for billions of years, will one by one burn out, gently fading away. They will leave behind the quiet remnants of their lives, dense white dwarfs, incredibly compact neutron stars, and the enigmatic black holes. Galaxies themselves will continue to evolve, gently merging and cannibalizing smaller galaxies, growing ever larger, and their stellar populations will continue to age. Over even longer stretches of time, in the unimaginable distances of the far future, even black holes are expected to slowly evaporate through a process theorized by Stephen Hawking, known as Hawking radiation. Eventually, the universe would be left filled with only a diffuse sea of low-energy photons and the occasional lonely subatomic particle, a cosmic stillness. These visions of the universe's ultimate future are extrapolations, gentle predictions, based on our best theoretical models and the observations we have meticulously gathered. As our understanding of dark energy, dark matter, and the universe's fundamental laws deepens and becomes more refined, our predictions may subtly evolve, perhaps revealing new possibilities or dismissing old ones. The study of cosmology remains a wonderfully dynamic field, a continuous process of discovery where each new piece of evidence, each new insight, has the profound potential to alter our perspective on the universe's past, its vibrant present, and its whispered future. It's a testament to our ongoing quest to understand the grand narrative in which we find ourselves. Continuing our cosmic journey, we turn our gaze closer to home, to the familiar spirals of our own galaxy, the Milky Way. This majestic spiral galaxy, teeming with billions of stars, countless planets, and shimmering nebulae, is not a static island in space. It is on a dynamic trajectory, a celestial dance that is both fascinating and inevitable, shaped by the very same cosmic forces, gravity, and expansion that govern the universe at large. Our galactic home has a story that continues to unfold, a future that is already being written by the silent pull of cosmic tides. The Milky Way is currently on a gentle yet inexorable collision course with our nearest galactic neighbor, the Andromeda Galaxy M31. Imagine two graceful cosmic dancers, slowly, patiently drawing closer to each other across the vast cosmic ballroom. Astronomical observations meticulously gathered over years and sophisticated computer simulations which allow us to rewind and fast forward the cosmic film predict that in about 4 billion years, the Milky Way and Andromeda will engage in a truly titanic, yet surprisingly gentle merger. This event, far from being a catastrophic destructive collision, as we might imagine with everyday objects, will be a gradual, elegant process unfolding slowly over hundreds of millions of years to complete. The immense distances between individual stars within galaxies mean that direct star-on-star collisions are incredibly unlikely, almost impossible. Instead, the overwhelming gravitational forces between the two galaxies will subtly warp and reshape them, pulling at their spiral arms, stirring their gas and dust. Eventually, they will coalesce, merging into a single, much larger elliptical galaxy, often affectionately referred to as Milkomeda or Milkdromeda. It will be a new, grander galactic form, a testament to the transformative power of gravity. During this magnificent galactic merger, the vast gas and dust clouds within both galaxies will interact, gently compressing each other. This compression will act as a trigger, sparking a spectacular new burst of star formation. Imagine regions of the newly merging galaxy suddenly flaring into brilliant light as countless new stars are born from the colliding gas. Some regions will become denser, forming new stellar clusters sparkling like jewels. Meanwhile, other areas of gas and stars may be gently stripped away, contributing to the formation of long, elegant tidal tails, elongated streams of stars and gas pulled out from the merging galaxies by the powerful gravitational forces stretching like ghostly arms into the void. Simultaneously, the supermassive black holes at the very center of each galaxy, the quiet gravitational anchors, will gradually begin to spiral towards each other. This will be a slow, patient descent, lasting millions of years, until they eventually merge to form an even more massive colossal black hole at the heart of the new Milkomeda galaxy. The fate of our own solar system in this grand cosmic dance remains gently uncertain. The Sun and its planets could theoretically be flung into a new region of the resulting Milkomeda galaxy, perhaps much farther from the galactic core, drifting into a quieter, more isolated cosmic neighborhood. Or they could remain relatively undisturbed, continuing in an orbit similar to their current one, simply residing within a larger, reshaped galaxy. However, by the time the Milky Way and Andromeda merger truly begins to take shape in those distant billions of years, our Sun will have already entered the final gentle stages of its own life cycle. It will have swollen into a luminous red giant, engulfing its inner planets before gently shedding its outer layers to leave behind a cooling, quiet white dwarf star, the compact remnant of its former self. Beyond the immediate drama of the Milky Way-Andromeda merger, the long-term fate of Milkomeda will continue to be influenced by the same dark energy that is relentlessly driving the universe's grand expansion. As galaxies outside our local supercluster, those beyond the gravitational embrace of Milkomeda, move away from us more rapidly. Our newly formed supergalaxy will become increasingly isolated in a universe where distant galaxies recede beyond our detectable horizons. Over trillions of years in the quiet depths of cosmic time, star formation will gradually cease within Milkomeda as the available gas is slowly used up or gently expelled. This will leave a galaxy populated primarily by aging, fading stars, cold white dwarfs, silent neutron stars, and the ever-present enigmatic black holes. In this grand, sweeping cosmic narrative, the Milky Way's story is a beautiful, enduring testament to the dynamic and ever-changing nature of the universe. Galaxies are not static, unchanging islands in the cosmos. Instead, they are vibrant, evolving entities that merge, reshape, form new structures, and give birth to countless stars and perhaps countless instances of life. Their quiet dance continues an eternal testament to the universe's ceaseless evolution. Building on the narrative of the Milky Way's eventual merger with the Andromeda Galaxy, let's delve deeper into the cosmic ballet of galaxies colliding and merging, a fundamental transformative process that shapes the universe's structure and evolution. This phenomenon, while it might evoke images of catastrophic violent explosions in our minds, actually unfolds over vast timescales and immense distances governed by the inexorable yet surprisingly gentle pull of gravity. It is less like a head-on crash and more like a slow, graceful embrace, a dance lasting millions upon millions of years. Galaxy collisions are a natural, inevitable consequence of the universal gravitational attraction between galaxies that find themselves in relatively close proximity to each other. As galaxies drift through the vast, mostly empty expanse of space, their mutual gravitational forces slowly, gently draw them together, pulling them into a cosmic embrace. Despite the vast, almost unimaginable distances between individual stars within galaxies, stars are so far apart that the chances of two of them actually colliding during a galactic merger are incredibly, vanishingly small. Like two tiny specks of dust trying to hit each other in an entire continent. It is not the stars themselves that collide. Instead, it is the powerful gravitational forces between the two immense galactic systems that dramatically alter their structures, pulling and tugging at their very fabric. The initial stage of a galaxy merger often involves the interaction of the galaxy's outer halos. These halos, vast diffuse regions surrounding the visible galactic disks, are composed primarily of dark matter, but also contain scattered stars and tenuous gas. As these halos begin to overlap and interact, they exert powerful tidal forces on each other. These forces, like an unseen cosmic hand, can dramatically distort the galaxy's elegant shapes, stretching and pulling out long shimmering streams of stars and gas into vast, beautiful arcs. This initial gravitational tug-of-war can also paradoxically trigger intense bursts of new star formation. as gas clouds within the galaxy's spiral arms are gently compressed by the gravitational interactions. They become denser, hotter, and collapse more readily, igniting nuclear fusion in their cores and giving birth to countless new stars. It's a creative destruction, a beautiful, fiery consequence of the cosmic embrace. As the galaxies draw ever closer, their gravitational interaction becomes more intense and intimate. They may pass directly through each other not once, but multiple times, their gravitational fields powerfully stirring up their internal structures and leading to further, more dramatic bursts of star formation. Over immense stretches of time, the galaxy's mutual gravity slowly, patiently slows their relative motion, causing them to oscillate back and forth like cosmic pendulums. With each pass, they gradually lose orbital energy, transferring it to their stars and gas, allowing them to draw closer and closer together. During these complex, drawn-out encounters, the supermassive black holes residing at the center of each galaxy, if present, will begin to profoundly influence the merger process. These colossal black holes, the gravitational hearts of their respective galaxies, will gradually spiral towards each other in a slow, majestic dance, eventually sinking to the very center of the newly forming, merged galaxy. Their final colossal embrace, when they eventually merge, will release unimaginable amounts of energy, potentially producing powerful jets of high-energy particles that stream out into the cosmos. The final stage of the merger culminates in the galaxies slowly, gently coalescing into a single, unified entity. The appearance of this resulting galaxy can vary greatly depending on the original galaxy's masses, their sizes, their gas content, and the precise angle of their approach. They can transform from elegant spirals into grand, often more rounded elliptical galaxies, which tend to have less gas and dust remaining for new star formation. Or if enough angular momentum is preserved, they might form a new, even larger spiral galaxy. Throughout this entire process, dark matter plays an absolutely crucial foundational role. It acts as the invisible scaffolding, both in drawing galaxies together through its immense gravitational pull and in influencing the intricate dynamics of the merger itself. The distribution of dark matter around galaxies helps to gently guide their motion and interaction profoundly, influencing the ultimate outcome and the final shape of the merged cosmic city. Galaxy mergers are not isolated, rare events, but are in fact an intrinsic natural part of the ongoing evolution of the universe. They are a primary driver of the growth of galaxies, allowing them to build up their immense stellar populations over cosmic time. They intensely influence the rate of star formation, sometimes triggering it, sometimes suppressing it, and they contribute significantly to the complex interplay of processes that continuously shape the cosmic landscape. Observations of these magnificent colliding and merging galaxies across the universe, captured by our most powerful telescopes, not only provide us with truly spectacular, awe-inspiring images, but also offer critical, invaluable insights into the very life cycle of galaxies, the mysterious behavior of dark matter, and the fundamental unwavering gravitational forces that gracefully orchestrate the entire cosmos. It is a slow, powerful dance of creation and transformation happening continuously across the vastness of space. Journeying into our next chapter, we enter a more philosophical realm, pondering a question that beautifully bridges the realms of science, ethics, and profound philosophy. Should we try to contact extraterrestrial life? This profound inquiry taps into the very core of the human spirit of exploration and curiosity that has always driven us to peer into the night sky, to send our ingenious spacecraft to distant planets, and to patiently scan the cosmos for the faintest signals of other civilizations. Yet it also confronts us with profound uncertainties about the very nature of extraterrestrial life and the immense, largely unknown possible consequences of making contact. It's a question that whispers to us from the cosmic void, filled with both hope and apprehension. The search for extraterrestrial intelligence, CD, has been an ongoing, patient scientific endeavor for decades. Using immense radio telescopes, like colossal ears, listening to the silence of space scientists have been carefully listening for artificial signals, deliberate broadcasts that might indicate the presence of intelligent life beyond Earth. Some initiatives have, even with a touch of cosmic bravery, sent carefully crafted messages out into space, aiming to communicate our very existence to potential extraterrestrial civilizations. These efforts are gently grounded in a deep universal hope, the hope that we are not alone in this vast cosmic ocean. The discovery of other forms of intelligent life would undoubtedly be one of humanity's most profound and transformative discoveries, offering unparalleled insights into the nature of life itself, the very essence of intelligence, and our unique place in the grand tapestry of the cosmos. It could be a moment that redefines everything we know. However, the question of whether we should actively try to contact extraterrestrial life is fraught with deep, thoughtful debate. On one side, an argument in favor gently suggests that making contact could lead to an extraordinary exchange of knowledge and culture. Imagine the possibilities and exchange that could immensely enrich our understanding of the universe, of physics, of biology, and indeed of ourselves. The potential for scientific and technological advancements is truly immense, almost boundless, possibly offering elegant solutions to some of the most pressing challenges we face here on Earth, from climate change to disease. Or it could open entirely new avenues of inquiry into the fundamental laws of physics, the mysteries of biology, and the very nature of consciousness itself. It is a compelling vision of universal enlightenment. On the other hand, there are significant sober concerns and risks associated with attempting to contact extraterrestrial civilizations. History sadly offers us cautionary tales. The history of human exploration and colonization on Earth provides stark lessons of encounters between civilizations with vastly disparate levels of technology and understanding. All too often, these encounters have led to the exploitation, or even the decimation, of the less technologically advanced societies. The unsettling possibility that extraterrestrial civilizations might be far, far more advanced than us, having had billions of years longer to evolve, raises profound questions about their intentions and how they might perceive or choose to interact with us. Would they be benevolent guides or something else entirely? We simply do not know. Furthermore, the incredible diversity of life on Earth itself gently suggests that extraterrestrial life forms, if they exist, could be vastly, unimaginably different from us, not only biologically, but also in their perceptions, their values, and their very methods of communication. These fundamental differences raise deep ethical considerations about the inherent right to initiate contact without a broad global consensus. What right do we have to speak for all of humanity, or indeed for all life on Earth? And what might be the potential unforeseen impact on humanity, on our fragile societies, and on the Earth's delicate biosphere? These are not questions to be taken lightly. Philosophical considerations also play a crucial introspective role in this profound debate. The very act of reaching out to the cosmos is a powerful reflection of our innate human desire to understand our own existential questions, to find our unique place in the universe. Yet it also quietly requires us to consider the immense responsibility that comes with such an endeavor. We must contemplate the implications not only for our own species, but for any other beings we might encounter. It asks us to balance our inherent curiosity with a deep, thoughtful caution. In contemplating whether we should actively try to contact extraterrestrial life, we are gently challenged to balance our innate curiosity and our relentless quest for knowledge with a thoughtful, humble consideration of the potential risks and complex ethical dilemmas. This question invites a truly multidisciplinary dialogue, encompassing not only the cutting-edge scientific and technological aspects, but also the timeless philosophical, ethical, and profound social dimensions of our place in the cosmic whole. Diving further into this profound topic, we find ourselves faced with the deep, pervasive impact the vastness of the universe has on our philosophical outlook. This immense expanse, filled with billions of galaxies, each home to billions of stars, and potentially countless planets, stretches our imagination to its very limits and challenges our deepest understanding of existence itself. It prompts a quiet, profound reevaluation of human significance, of the very nature of life, and of our timeless search for meaning in a cosmos that is so incredibly grand. The stark realization of the universe's immense vastness gently brings to light our physical insignificance within the cosmic scale. Our beautiful Earth is but a tiny speck, a pale blue dot in our galactic neighborhood. And that neighborhood itself is just a minute fraction of the entire observable universe. This perspective can evoke a powerful sense of humility, highlighting the incredible fragility and preciousness of life on our planet. It underscores the truly remarkable coincidence of conditions that have allowed life to flourish here, thriving in stark contrast to the seemingly inhospitable silent vastness of space that surrounds us. It reminds us that our home is a precious, delicate oasis. Simultaneously, the universe's sheer enormity and breathtaking complexity inspire deep awe and wonder, fueling our innate curiosity and driving both scientific and philosophical inquiry. The relentless pursuit of understanding the cosmos serves as a powerful testament to the resilience of the human spirit and our endless quest for knowledge. It gently challenges us to push the boundaries of our cognitive and technological capabilities, seeking not only to uncover the deepest mysteries of the universe, but also to explore the profound depths of human consciousness and the very limits of our reason. It is a journey of both external and internal discovery. The possibility of other life forms perhaps flourishing on countless worlds scattered across distant galaxies invites us to ponder the universality of experiences such as consciousness, morality, and that shared human search for meaning. It raises fascinating questions about the potential for communication and profound understanding between vastly different forms of life, and the implications for our concepts of morality rights and the intrinsic interconnectedness of all beings in the cosmos. The discovery of extraterrestrial life would not only revolutionize our scientific understanding, but would fundamentally alter our philosophical and ethical frameworks, gently challenging anthropocentric views and expanding our very conception of the community of life, drawing us into a much grander family. On a more existential level, the vastness of the universe profoundly confronts us with the temporal and spatial limits of our own existence. It forces us to grapple with immense questions about the beginning and end of the universe, the enigmatic nature of time itself and our place within this grand unfolding continuum. The humbling realization that the universe has existed for billions of years before us and will continue its journey long after we are gone can evoke a powerful search for meaning and purpose that transcends individual lives. It leads to deep reflections on legacy, on memory, and on the lasting impact of our actions on future generations, and indeed, on the cosmos itself. It is a quiet call to contribute our own small precious thread to the cosmic tapestry, continuing on from the theory of everything that grand quest to unify all fundamental forces. We gently delve into how quantum mechanics itself intricately relates to the cosmos. Quantum mechanics, a fundamental theory in physics, provides a deep, almost mystical description of the physical properties of nature at the scale of atoms and subatomic particles. At first glance, it might seem worlds apart from the vastness of the cosmos, like a tiny whisper lost in an infinite roar. Yet its principles are deeply, beautifully woven into the very fabric of the universe, subtly influencing cosmic evolution and structure in profound ways. At the heart of quantum mechanics are principles such as uncertainty and superposition, which dictate that particles can exist in multiple states simultaneously until observed, challenging our classical everyday notions of reality. These principles aren't just for laboratory experiments. They're crucial to understanding processes that unfold on immense cosmic scales. For example, the very nuclear fusion that powers stars, including our own life-giving sun, is governed by quantum tunneling, a fascinating phenomenon that allows particles to, in a sense, tunnel through energy barriers they shouldn't classically be able to cross. Without this quiet quantum effect, stars simply would not ignite, and the universe as we know it, teeming with light and life, would not exist. Quantum mechanics also played a vital foundational role in the early universe. Shortly after the Big Bang, when the universe was an incredibly hot, dense plasma, tiny quantum fluctuations, minute variations in energy occurred. These fluctuations, magnified to cosmic proportions by the incredible speed of cosmic inflation, became the very seeds for the large-scale structure of the universe, eventually leading to the formation of galaxies and galaxy clusters. The grand distribution of matter across the universe, from the subtle patterns in the cosmic microwave background radiation to the intricate cosmic web of galaxies, still bears the faint, indelible imprint of these initial quantum ripples. Furthermore, quantum mechanics is key to understanding black holes. Those enigmatic points where gravity is so strong that not even light can escape. Stephen Hawking's pioneering work on black holes showed that due to subtle quantum effects near their event horizons, black holes can slowly, quietly emit radiation, a phenomenon now known as Hawking radiation. This profound revelation gracefully bridges the seemingly vast gap between quantum mechanics and general relativity, offering tantalizing insights into how quantum principles apply under the most extreme gravitational conditions. Even the intriguing concept of dark matter, which mysteriously holds galaxies together yet emits no light, gently invites quantum explanations. Several hypothetical particles that could constitute dark matter, such as WIMPs. Weakly interacting massive particles, or axions, arise from theories that extend the standard model of particle physics, which is itself deeply grounded in quantum mechanics. The search for these particles involves understanding their quantum properties and how they subtly interact with the gravitational forces that shape the cosmos. On our journey through the realms of quantum mechanics and the cosmos, we naturally progress to a question that has captivated human imagination across cultures and ages. Is time travel theoretically possible? Within the elegant framework of modern physics, the concept of time travel is not merely the stuff of whimsical science fiction, but a serious scientific inquiry that intimately intersects with our deepest understanding of the universe's fundamental laws. The theory of relativity, developed by Albert Einstein, provides the most significant theoretical foundation for even considering time travel. According to general relativity, the very fabric of space-time is curved and warped by mass and energy, and this curvature dictates how objects move through both space and time. Remarkably, the equations of general relativity allow for exotic solutions where space-time could curve back on itself, forming loops known as closed time-like curves. These theoretical structures could in principle permit a path from a point in space-time to the past or future, and then gracefully back to the original point, suggesting a fascinating possibility for time travel. One hypothetical structure that could allow for such time travel is the wormhole, a bridge or tunnel through space-time that could connect distant parts of the universe or even different times. If a wormhole could be stabilized with exotic matter, which possesses negative energy density, a very strange property, it might be possible, in theory, to traverse it and achieve time travel. However, the existence of stable traversable wormholes and exotic matter has not been proven, and the practical challenges of creating or finding a wormhole, let alone safely traveling through one, remain formidable, whispering of difficulties far beyond our current grasp. Another concept related to time travel arises from the idea of cosmic strings, hypothetical defects in space-time unimaginably thin but incredibly dense, left over from the very early universe. If two cosmic strings were to pass incredibly close to each other, or if a single cosmic string were to move in a loop at a significant fraction of the speed of light, they could theoretically create localized conditions that allow for time travel to the past. Despite these intriguing theoretical possibilities, time travel faces numerous profound scientific and philosophical challenges. For one, the famous paradoxes associated with time travel, such as the grandfather paradox, where a time traveler could potentially prevent their own existence by altering the past, raise deep questions about causality and the very nature of time itself. Moreover, The immense energy scales required for manipulating space-time to achieve time travel are currently far, far beyond human reach. Quantum mechanics also subtly enters the discussion of time travel, particularly through the concept of quantum entanglement, which suggests a form of communication between particles that is instantaneous and independent of distance. Some interpretations of quantum mechanics propose that entangled particles are connected by microscopic wormholes, hinting at a quantum foundation for space-time structures that could theoretically allow for time travel. However, leveraging such phenomena for macroscopic human-scale time travel remains pure speculation. Now let us ask an interesting question, one that has captivated human imagination across cultures and ages. Could life exist elsewhere in the universe? This query not only probes the limits of our understanding of life itself, but also touches on profound philosophical implications about our unique place in the grand cosmos. The universe, as we've seen, is incredibly vast, with billions of galaxies, each containing billions of stars, and potentially even more planets. The Kepler Space Telescope and other missions have patiently discovered thousands of exoplanets, planets orbiting stars beyond our solar system. Many of these lie in the habitable zone, often affectionately called the Goldilocks zone, where conditions might be just right for liquid water, a crucial ingredient for life as we know it to exist on a planet's surface. These groundbreaking discoveries have significantly expanded our understanding of the potential cosmic habitats for life, gently suggesting that the conditions conducive to life could be far more common than previously imagined. The search for extraterrestrial life extends beyond distant exoplanets to our very own cosmic neighborhood, our solar system's planets and moons. Mars, with its compelling past evidence of water flow and the recent discovery of seasonal methane spikes in its thin atmosphere, has been a primary focus for intrepid missions seeking signs of past or present microbial life. Moons like Europa orbiting Jupiter and Enceladus orbiting Saturn with their hidden vast subsurface oceans warmed by tidal forces offer another tantalizing possibility for hosting life. These icy worlds draw plans for future missions to explore their hidden alien seas. Beyond our solar system, the painstaking study of exoplanet atmospheres, though still in its infancy, aims to detect biosignature gases, gases produced by living organisms that could accumulate in a planet's atmosphere. Detecting molecules like oxygen, methane, or ozone in concert could offer a potential indirect method of discovering life, a faint chemical whisper across interstellar space. The search for life also delves into the profound question of what form life might take elsewhere. The life we know here on Earth is exquisitely carbon-based, utilizing water as a vital solvent. However, scientists thoughtfully speculate about the intriguing possibility of alternative biochemistries, such as life forms based on silicon or life existing in environments with solvents other than water like methane or ammonia, perhaps in the frigid depths of Titan's lakes. This openness to alternative forms gently expands our understanding of what life truly means, acknowledging that it could exist under conditions vastly different from those on Earth, in forms that might be utterly unfamiliar to our terrestrial senses. Continuing our journey through the unknowns of space, our next topic brings us closer to home, exploring the magnificent instruments that serve as our windows to the universe telescopes. These marvels of engineering and science allow us to peer into the vastness of space from our neighboring planets to galaxies billions of light years away, profoundly aiding our quest to understand if life exists beyond Earth, and tirelessly uncovering the deepest mysteries of the cosmos. Telescopes work by collecting and focusing light or other forms of electromagnetic radiation from celestial objects to create an image. The larger a telescope's light collecting area, like a bigger bucket catching more rain, the more faint objects it can observe and the more subtle detail it can reveal. There are two primary types of telescopes, refracting and reflecting, each utilizing different elegant mechanisms to gather light. Refracting telescopes use lenses to bend and focus light. The main lens called the objective bends incoming light rays to converge at a focal point where the image is magnified and observed through an eyepiece. Historically significant refracting telescopes were the first type to be invented, with Galileo Galilei famously using one to make groundbreaking astronomical discoveries in the early 17th century, revealing the moons of Jupiter dancing around it. Reflecting telescopes, on the other hand, employ mirrors instead of lenses. A large curved mirror, known as the primary mirror, reflects light to a focal point. A secondary mirror may then redirect this light to an eyepiece or a camera. Reflecting telescopes offer several distinct advantages over refractors, including the elimination of chromatic aberration, a distortion seen in refractors where lenses break light into different colors, and the crucial ability to construct much larger telescopes as mirrors can be supported from behind, reducing sagging and deformation under their own weight. Beyond these traditional optical telescopes, remarkable advancements in technology have led to the development of specialized telescopes for observing non-visible forms of electromagnetic radiation, such as radio-infrared, ultraviolet X-ray, and gamma-ray telescopes. These instruments, acting as different kinds of cosmic senses, allow astronomers to explore aspects of the universe completely invisible to optical telescopes, from the cold, dark dust clouds, where new stars are slowly being born, to the violent high-energy environments around black holes and neutron stars. Radio telescopes, for example, use immense dish antennas to detect radio waves from space, providing unique insights into cosmic phenomena like pulsars, quasars, and the subtle hum of the cosmic microwave background radiation. Space-based telescopes, such as the iconic Hubble Space Telescope, operate above Earth's atmosphere, which absorbs or scatters much of the electromagnetic spectrum, offering an unobstructed crystal-clear view of the universe in optical ultraviolet and near-infrared light. The operation of telescopes, whether they are majestic ground-based observatories or delicate instruments orbiting in space, involves not just the collection of light, but also sophisticated data analysis techniques. The images and signals captured by telescopes are meticulously processed and analyzed, using complex computer algorithms patiently revealing details and structures not visible in the raw data. This analysis can involve precisely measuring the distance, chemical composition, temperature, and motion of celestial objects, all contributing to our ever-deepening understanding of the universe's structure, its grand evolution, and the fundamental laws of physics that orchestrate its every motion. Astronomers also use the ingenious technique of parallax to measure the distance to nearby stars. By observing how a star's position subtly shifts against the background of more distant stars as Earth orbits the Sun, like watching your thumb shift against a distant background, as you close one eye, then the other, scientists can precisely calculate its distance from us. This fundamental measurement forms the crucial first rung on the cosmic distance ladder, which is then used to determine the distances of far more remote objects in the universe. Now let's turn our focus to a monumental leap in our astronomical capabilities: the James Webb Space Telescope, JWST. Launched into space at the very end of 2021, the JWST represents the most sophisticated and powerful space telescope ever built, poised to unravel the deepest mysteries of the universe with unprecedented clarity and profound depth. It is our newest, most powerful eye, designed to peer into the very earliest moments of cosmic time. The JWST is a magnificent international collaboration gently led by NASA, with significant contributions from the European Space Agency ESA and the Canadian Space Agency CSA. It is exquisitely designed to observe the universe primarily in the infrared spectrum, allowing it to peer through the thick cosmic dust clouds that would completely obscure the view of optical telescopes, and to detect the incredibly faint light of the most distant stars and galaxies whose light has been stretched into the infrared by the expansion of the universe. With a primary mirror, 6.5 meters in diameter, comprised of 18 hexagonal gold-coated segments, the JWST boasts a light-gathering capacity more than 6 times that of its predecessor, the Hubble Space Telescope. This allows it to observe objects much, much further away, and therefore much, much further back in time than ever before, like a cosmic time machine reaching back to the dawn of creation. One of the JWST's primary and most ambitious objectives is to literally explore the edge of the observable universe, diligently seeking to observe the first galaxies that formed after the Big Bang over 13.5 billion years ago. By studying these nascent early galaxies, astronomers hope to learn more about the very formation and initial evolution of the first structures in the universe, shedding crucial light on the fundamental processes that led to the complex, intricate cosmic web of galaxies we see today. The JWST's extraordinary infrared capabilities are absolutely crucial for this task, as the light from these incredibly distant ancient galaxies has been significantly stretched into the infrared range by the vast expansion of the universe, a phenomenon known as redshift. In addition to exploring the earliest universe, the JWST will also undertake the groundbreaking task of studying the atmospheres of exoplanets, those worlds orbiting distant stars with the potential to identify tantalizing signs of habitability or even life itself. Its powerful instruments can meticulously analyze the chemical composition of exoplanet atmospheres, searching for subtle, telltale molecules like water vapor, carbon dioxide, and methane. The presence of these molecules, particularly when found together in specific ratios, could subtly indicate the presence of biological processes at work, a faint, chemical whisper of life across interstellar space. The JWST is also tasked with unraveling the profound mysteries of star and planet formation within our own galaxy. By observing the dense, cold molecular clouds where stars are slowly, patiently born, the telescope will provide unparalleled insights into the precise conditions and intricate processes that lead to the formation of stars and their accompanying planetary systems. This knowledge is not only fundamental to understanding our own solar system's origins, but also to comprehending the vast diversity of planetary systems that likely populate our galaxy. As the JWST continues its mission, it promises to truly transform our understanding of the universe, challenging existing theories, uncovering new phenomena, and providing answers to long-standing questions about the very nature of the cosmos, bringing us closer than ever to understanding the edge of the universe and our unique place within it. Over the past few decades, satellites have truly revolutionized astronomy, providing a unique vantage point beyond Earth's blurring atmosphere that is simply unattainable by even the most powerful ground-based observatories. From the meticulous mapping of the cosmic microwave background radiation to the groundbreaking discovery of countless exoplanets and the vigilant monitoring of dynamic cosmic phenomena, satellites have opened entirely new windows into the universe, each contributing unique insights that have immeasurably deepened our cosmic knowledge. The launch of the Hubble Space Telescope in 1990 marked a profound turning point in space exploration. Orbiting Earth blissfully free from the distortions of the atmosphere, Hubble has captured images of unparalleled clarity and breathtaking detail, truly revealing the universe's dynamic and intricate structure. Its patient observations have led to countless breakthroughs in our understanding of black holes, the precise age of the universe, the mysterious existence of dark energy, and the fundamental processes that govern the life cycles of stars. Hubble's deep field images, which show thousands of galaxies in what appeared to be empty patches of sky reaching back billions of light years, have provided a crucial glimpse into the universe's earliest stages, beautifully illustrating the evolution of galaxies over immense cosmic time. Another supremely significant satellite, the Cosmic Background Explorer COBE, launched in 1989, performed the meticulous task of mapping the cosmic microwave background radiation, that ancient afterglow of the Big Bang. COBE's precise measurements provided powerful, irrefutable evidence for the Big Bang theory, showing that the universe's background radiation is remarkably uniform with incredibly subtle variations that perfectly support our models of cosmic inflation. This profound discovery was pivotal, earning its principal investigators the Nobel Prize in Physics in 2006. Following COBE-E, the Wilkinson Microwave Anisotropy Probe, WMAP, and later the Planck satellite further refined measurements of the cosmic microwave background, producing maps with unprecedented precision. These observations have helped to precisely determine the universe's age, its ultimate shape, and its enigmatic composition, contributing to the standard model of cosmology that describes the universe as flat and overwhelmingly dominated by dark energy and dark matter. Satellites have also been absolutely instrumental in the burgeoning search for exoplanets. The Kepler Space Telescope, launched in 2009, was specifically designed to detect Earth-sized planets in the habitable zones of their stars where conditions might allow for liquid water to exist. Kepler tirelessly discovered thousands of exoplanets, beautifully revealing that our galaxy is teeming with a diverse array of worlds, many of which challenge our previous understanding of planet formation and the tantalizing potential for life beyond Earth. Furthermore, satellites dedicated to observing our own sun, such as the Solar Dynamics Observatory (SDO), have provided incredibly detailed knowledge of solar activity, including sunspots, solar flares, and colossal coronal mass ejections. These observations are crucial for understanding the sun's dynamic impact on space weather and its subtle yet profound influence on Earth's environment and technological systems. As we near the end of this journey through the cosmos, we arrive at the very end of our current understanding, stepping into the realm of our future, our possibilities, and our deepest ponderings. The universe remains a vast, mostly uncharted territory, a profound mystery that continually challenges our deepest scientific and philosophical inquiries. The very possibility of life elsewhere, a question that continues to echo through the silence of space, redefines our search for meaning and our place within this immense cosmic tapestry. The technological leaps envisioned for the future, from revolutionary propulsion systems to exquisitely sensitive new telescopes, promise to deepen our understanding and expand our reach further into the galaxy, and perhaps even beyond. What do you think is outside our universe? What mysteries still await our gentle gaze, our patient instruments, and our boundless curiosity? The next chapter in the human story interwoven with the cosmos is not yet written. It is filled with endless mystery, profound adventure, and the quiet promise of new discoveries. Thank you for listening, curious minds, as we gently drifted through the wonders of our universe.